oxymoron. So effectively, ceramics are toughened by a different technique, and as a lot of brittle materials are, which is what I call extrinsic toughening. This is something now that doesn't take place ahead of the crack tip, it takes place either at or behind the crack tip. And these are techniques which carry load or shield the crack from the driving force. And the ones that are the most effective, of course, are crack bridging, be it sort of grains in ceramics. There's a little picture of a ceramic grain in silicon carbide here, bridging, or this is basically how fiber composites work. And in fatigue, we have wedging effects that are called crack closure. These take place behind the crack tip and therefore are a function of the crack size. And that's extremely important. You've always got intrinsic toughening, but these extrinsic toughening mechanisms have to have a crack to operate. They, unlike occurring at the nanoscale, these can occur at multiple scales. You can have in bone, you can have extrinsic toughening at almost at the hundreds of microns dimensions. So this is really the sole way. There's a few strange ceramics, perhaps like the max phases, but most ceramics have to be, and brittle materials, if they're toughened, have to go this extrinsic route. And so when you have a toughening which is occurring in the wake, you automatically get an R curve. And I've been very sort of trying to push this concept of the toughness versus crack extension. There's a couple of R curves here for different materials. In toughness, everybody thinks of the crack initiation toughness, K1C and so forth. But in these materials, there's an awful lot of toughness here, which is basically what I would call the crack growth toughness. Now, it's not so easy to measure robustly with fraction mechanics. The R curve gets a little bit tenuous in terms of justifying in terms of fraction mechanics, but from a material science point of view and a materials development point of view, all this toughness is really important. So, as I said, the intrinsic ones generally apply to ductile materials, not uniquely, but mostly. The extrinsic ones apply more to brittle materials. But what has always fascinated me about natural materials is they seem to seamlessly combine both intrinsic and extrinsic mechanisms. And I want to just look at that in different materials as we go along, biological materials. And I think one of the reasons for this is that there's many different toughening mechanisms here, would be them intrinsic or extrinsic, and they're derived, their origin is at different length scales. And the average biological material has multiple length scales, so they can develop these different mechanisms quite easily. It's much a little bit more difficult in synthetic materials because we don't develop so many length scales. So let's look at some of these things. Just quickly, to be able to do this, you need to move from the macro to the nanoscale. This is preaching to the choir, of course, to this audience, but this is what I do. I try to use fraction mechanics properly at the macro scale. We use a lot of in situ computed X-ray tomography. It's a nice 3D technique. The beam lines at Berkeley are a little bit, they're more soft X-rays, so I can't do metals in that regard, but I'll show you some ceramics and so forth. I like to use in situ SEM testing as well. You don't quite have the three-dimensional resolution of three-dimensional aspects of tomography, but you can certainly get higher resolution. And a lot of fracture is understood at the microscale, so you'll see a little bit of that. I'll talk about in situ small angle X-ray scattering and wide angle X-ray diffraction, which is a great technique for looking at biological materials where you can do tensile tests in the beam line. And lastly, one of my things I found interesting is to use TEM techniques to look at fraction. Now, I've always turned my nose up at people who do that because, of course, you have a very thin sample, so all the stress states are wrong and so forth. But you can see things in the TEM that you can't see with any other technique. So I think it's interesting to at least look, and then you can debate afterwards about whether you're looking at an artifact of the thin film or whether it's a real effect. So we'll talk a little bit about these techniques, particularly in metals at the end of the talk. So that's sort of my roadmap. So let's start with bone. And this is just a nice depiction of the multiple length scales of bone. And this is a crack propagating in, it's actually antler bone, but you can see these are very complex cracking configurations. So let's look a little bit at that. So as I said, bone has these hierarchies of structure. Sometimes they're called the 7 hierarchies. At the nanoscale, you're dealing with a sort of peptide chains that are twisted to form collagen, and the collagen fibrils are then twisted to form a collagen fiber. These fibrils have mineral deposited on them in a particular spacing, which is actually very useful. So they're mineralized collagen fibrils. And then as you go up from microns to tens of microns, these fibrils are basically twisted to form fibers. And then when you get to the much coarser scales, you have this Haversian structure. We're now in the hundreds of microns, which is the way that bone remodels. And then there's the bone itself. There's the cortical bone on the outside and the trabecular bone on the inside. So there's a whole vast spectrum from nanometers to tens of centimeters where you can generate different structure. So I looked at this a few years ago with Marcus Buehler, actually, to look and see how you can characterize the toughening mechanisms in bone. And this intrinsic-extrinsic notion works very well, because if you look ahead of the crack tip, which is the intrinsic region, you're dealing with primarily plasticity mechanisms, which originate generally at smaller scales, below a micron, certainly. And there are many mechanisms, but the one that's the most important, I think, in bone is simply the collagen. The collagen stretches, and then you get what's called fibrillar sliding as the collagen slides apart. That is the main plasticity mechanism in bone. It also microcracks, which has an inelastic effect, but that fibrillar sliding is really important. And of course, anything which stops those fibrils from sliding apart is basically a mechanism that limits ductility. So this is very much in the intrinsic sense, but then if you go above a micron and you look at behind the crack tip, you get all these extrinsic mechanisms that remind you of a ceramic. First of all, the material microcracks. That's a plasticity type mechanism, but it's not really a toughening mechanism. It's not like in ceramics, it's not particularly potent, but it leads to other mechanisms. And when cracks grow in bone, they're growing into a sea of microcracks. And so at any time, if you freeze frame, you'll see little regions between the microcrack, which are bridges. And I call these uncracked ligament bridges, not ligament in the anatomical sense, but it's the little regions that are unbroken. And in fact, a lot of these microcracks are bridged with collagen fibrils. And of course, there's deflection. The bone has these osteonal structures where they remodel. They're these sort of long, they're generally along the axis of the bone. And the boundaries of these osteons are basically somewhat higher mineralized, so cracks tend to deflect at these boundaries. So there's a strong effect of deflection. So, you know, this is very much intrinsic, plasticity related, yet at these higher scales, these are all the sort of mechanisms that people like David Clark and Tony Evans modeled decades ago. So it's intriguing that again, nature can design materials with these multiple mechanisms. So if we look at these, this is using tomography. This is a picture of a deflected crack in bone. These orange things are the osteons, which are along the axis of the bone. It's being loaded along the axis, so the crack should grow, if it behaved itself, perpendicular to the maximum tensile stress. But the crack in white, you can see, has a highly deflected path. It deflects as it encounters the osteons. And so you get this high deflected path, and actually it's twisting as well, which gives it even more toughening potential. But there's a deflection one. If we propagate the crack in the other orientation, so now the osteons are, the main osteons are in this direction. These little linking ones, I forgot, they're called bands, something, I forgot what they're called, but the main osteons are here. The crack is growing parallel to them in this particular orientation, in this figure. This is a three-dimensional tomograph. This is the crack in this white region here, and the front of the crack is here, but everything in dark blue is unbroken, and you can see these regions behind the crack tip, which are these, what I call uncracked ligaments, and these little regions between the microcracks. So there's these very interesting mechanisms by which you can toughen bone intrinsically by the plasticity of the collagen and extrinsically by bridging and crack deflection. So this is just another picture of that. This is a two-dimensional image there, the osteons, and the crack is deflecting as it's counting the osteons. And there are these uncracked ligaments that form between the microcracks for a crack growing typically along the axis, the longitudinal axis of the bone. I have a movie of this, and let me just show you this. This crack is growing and it will encounter an osteon here, and you can see how it deflects and then forms a very complex fracture pattern, which is actually good for toughness. You'll also notice if you look along the osteon boundary opens up, and if you look very carefully, you'll see little fibrils that bridge the crack. So a lot of the mechanisms I've talked about are there. You can see now it encounters the osteon, you see the little fibrils bridging that osteonal crack, and then you get these really complicated fracture patterns. So this is a gross scale, but this can occur on a much smaller scale in real bone, and you can see it again. The osteon is a huge boundary that causes gross deflection of the crack. So how does this pertain to bone disease and so forth? Well, again, I don't know the full biological underpinnings of this. From an engineering point of view, it's quite a fairly straightforward picture. This is, first of all, the effect of aging on bone. This is an R curve of little fraction toughness tests. Young bone, 30-year-old bone, middle-aged bone, 50, 60-year-old bone, and the old bone is in the 80 to 90-year-old. And you can see there's a steady degradation in the toughness. Actually, the initiation toughness is less affected than the crack growth toughness. You know, there's a big issue in bone research. Everything was thought to be due to the bone quantity, that your bone's more likely to break when you get older because there's less bone there. Your bone mass diminishes. That's absolutely true, it does. But now people think that that's probably not as important as the quality of the bone. So, you know, the bone quantity is a civil engineering problem. It's, you know, you've got a structure and you're losing bits and pieces of it. But the bone quality is more of a material science subject. So that's what we looked at. So why is there this degradation? Well, again, you can look in the intrinsic and extrinsic notion. Extrinsically, I'm looking here at these little bridges that I talked about that are formed with the cracks forming at the osteonal boundaries. This is in young bone, but if you look at old bone, and these are tomographs, and these colored regions here are the osteons, and the color represents their width. Young versus old, you can see that there's far greater density of osteons as you get older, excessive remodeling and so forth. And since these little microcracks form at the osteonal boundaries, when you have a higher density of osteons, the bridges become much less effective. They're much smaller. So they're still there, but they're very much smaller than they were in young bone. So we think one of the effects of the extrinsic toughness degradation with age is simply the limiting role of these bridging mechanisms, which are associated with these little uncracked ligaments. What about the intrinsic part? Well, the intrinsic part, again, we're talking about the plasticity and the collagen. We use a kind of neat technique in the synchrotron. We take a tensile sample and we do a tensile test in the beamline, and then we measure, we do a small angle X-ray diffraction and a wide angle, small angle X-ray scattering, wide angle X-ray diffraction. The wide angle focuses on the mineral, which is of course hydroxyapatite, it's crystalline, and we can measure then by looking at the change in those patterns, the strain in the mineral. That's not so important here, but the small angle X-ray scattering looks at the collagen. And the collagen, if you remember, I said had mineral deposited on it, and it has it's a particular spacing. It's called the D spacing, and it's about 64 nanometers. And that acts as a little nanoscale strain gauge. So we can measure the strain in the collagen from the scattering on the small angle X-ray scattering measurement. So during a tensile test in bone, we can measure the strain in the bone. That's the regular strain in the bone, but we can actually measure the individual strains in the collagen versus the mineral. So what I'm trying to plot here is the strain in the collagen versus the strain in the sample. So let's just take an example at 1% strain, macroscopic strain in the sample. In young bone, most of that strain is carried by the collagen. The mineral is very hard and stiff, but the collagen is able to stretch and it's able to get to fibrillar sliding. But when you go to old bone, and this is the 80-year-old bone, the amount of strain in the collagen drops dramatically. So this is like an embrittlement. You've limited the ductility, and this fibrillar sliding is apparently less prevalent, and so you've limited your plasticity in the bone. Why is that? Well, it's a long story, but it's associated with cross-linking of the collagen. There are many types of cross-links in bone. These are associated with glycation end products. You know, glycation is the accumulation of sugars, and this is what leads to these cross-links. And so this fibrillar sliding is much less effective, and that's like you've limited the plasticity intrinsically. So that's the other mechanism which degrades the toughness of bone. So bone, like many biological materials, can develop intrinsic and extrinsic toughening, but by the same token, they can degrade. Now, there's a lot of sort of diseases of bone we've looked at, and I don't want to go through all the gory details, but this story is quite prevalent throughout. Again, doesn't describe the biological source of this, but it does provide some explanation of why we see these degraded toughness in bone. This is the brittle bone disease, osteogender imperfecta. This was done by a student who came over from Imperial called Alexander Carrero. And this is a horrible disease that affects children, and it leads to higher mineral content. There's increased turnover of the bone, and it becomes far more prone to fracture. We looked at this in a mouse model, and we looked at what happens to the toughness, looking at the intrinsic effect. These are stress strain curves, just normal stress strain curves. The wild type is the healthy bone, and this OIM plus and OIM are the severe disease and the mild disease. And what you can see is that when you compare the stress strain curves, that the degree of ductility is diminished, and a bit of the strength as well, by the disease. And so when you look at the cross-linking in these bones, we found there's a much higher degree of cross-linking in the diseased bone, which of course limits the ductility, just like it would in an embrittlement in a metal. So that's the intrinsic effect. You've not enabled this fibrillar sliding to be so effective. Then we look at the extrinsic effect. We just did toughness tests. This is an R curve again, and the wild type is the healthy bone, and this is the mild disease, and this is the severe disease. And you can see there's a big drop in the toughness, the intrinsic toughness, which is more probably related to this intrinsic effect, but the amount of crack extension prior to fracture is much, much more limited in the diseased bone, has a much lower toughness. Why is that? Well, if we look at the fracture surfaces, in the wild type material, in the healthy bone, you get the cracks deflecting. Now, they're not osteons in mouse bone, but they have their hypermineralized regions. So the crack encounters these things and deflects along the axis of the bone, which is a dramatic deflection. It's almost 90 degrees. And so that really is very good from the perspective of toughening the bone. You can see the fracture surface has this, it's where the crack is deflected. But in the diseased bone, there's no evidence of deflection. The crack just runs straight through and you get a very, very flat fracture. Now, just in terms of deflection, there's almost a factor of 2 in the stress intensity to propagate a straight crack versus a deflected crack. And this is primarily the reason. And we think this is due to the fact that this disease gives you a much higher mineral content in the grains. And so these hypermineralized interfaces, or the osteons in human bone, are nothing different from the matrix, because the matrix has become very mineralized itself. So you don't see these deflected regions. The bone becomes less homogeneous, basically. So this lack of deflection you'll see in many other diseases. Another one here, this is vitamin D deficiency. if we look at the difference between a bone that is deficient in vitamin D versus one that isn't, this was taken from biopsies. This is the R curves here. There's a lot of data and it's difficult to look at it, but there is a reduction in the toughness associated with the vitamin deficient bone. And one of the things that this does is it impairs the calcium absorption. You get unmineralized bone matrix, which is not able to mineralize properly, and it gets trapped basically as the bone develops. And so vitamin D deficient bone basically ages prematurely, and that's what the effects is. And so things I talked about before, the premature aging means that there's a much bigger increase in cross-linking. This is a measure of the cross-link, and this is in the deficient bone, this is in the normal bone. There's an elevation in the cross-linking, and of course that limits the plasticity, and we get this deflection effect again. These are beautiful pictures that are almost unintelligible, but this is looking at the normal bone. They're the osteons, and the crack is coming here. These are tomographs. I had to draw a little schematic here, but the cracks deflect along the osteonal boundaries in normal bone. But when you look at this vitamin D deficient bone, the cracks move around a bit, but they tend to propagate more without so much deflection. And again, we believe that's because in normal bone, these osteonal interfaces are highly mineralized, which means they're a prime place for deflection. But in the diseased bone, there's far more mineral in the matrix and these unmineralized regions that you don't get the same deflection. Intrinsic effects, extrinsic effects, one limits the plasticity by cross-linking, the other one limits the propensity for deflection, which reduces the extrinsic effect. Again, we don't know, I don't know, I'm not a biologist, I don't know the biological origin of these effects, but this is what I think causes these changes in the fragility of the bone due to aging or disease. We've also looked at this atypical femoral fractures. This is a really peculiar event that you can take these bisphosphonates. It's a way of inhibiting osteoporosis when you get older. The bisphosphonates basically prevent the bone from resorbing, so they act on the bone quantity, but in a very small portion of the population, they lead to these atypical femoral fractures, which are horrible fractures. They're very clean fractures of the femur, particularly in younger people, which is really bizarre. And although it doesn't affect a lot of the population, they're sufficiently traumatic that people have effectively, the use of bisphosphonates has dropped considerably, which is a great shame because it's an effective drug against the bone quantity issue. But we've looked at this and we've actually got biopsies. This is with Eve Donnelly at Cornell, and we've shown that in people that are susceptible to these fractures when they take bisphosphonates, the cracks simply don't deflect. They run through in a very linear fashion, whereas in people who don't take the bisphosphonates or they are not susceptible to this problem, you see the classic crack deflections. The red here is the simulated image here. So in all this is the non-bisphosphonated or people who are not affected by it. You get this deflection, which is highly good for toughening, but in the people that are susceptible to this problem, the cracks just don't deflect at all. And you can see these are very clean fractures. Now, why a certain part of the portion of the population who take these particular drugs are susceptible to this phenomenon, no one seems to know at this point. But again, we've shown, as others have shown, that there is an intrinsic effect. There's an increasing cross-linking when you take the bisphosphonates, but we don't quite know why there's a suppression in people who are susceptible due to crack deflection. So let's move on to different biological fields. These are fish scales. This is work that I've been doing with Mark Myers and his team, particularly Wen Yang down in UC San Diego. This is a pretty amazing material when you try to break a fish scale. This goes on for a while, so we'll move on, but they're pretty tough materials. We've looked at a number of different fish. Fish scales are interesting. They tend to be overlapping, which gives the fish flexibility, but they have a simple design. They have a very hard surface, which is effectively to prevent penetration, just like any armor would be. But then the lower portion, the subportion of the fish scale, is much tougher. So you need the hard region to prevent penetration of a tooth or something like that, but you need the lower portion to have toughness to accumulate all that excessive deformation. Now, if we did that, we tend to put a hard layer on top of a soft layer or a tough layer to generate that effect. But of course, nature does it by means of a gradient. This is in this particular scale, which is the alligator gar. It's all mineralized collagen, but the mineral content is much higher near the surface. You can see it's much, much harder. And as you go down into the scale, there's this beautiful gradient where the mineral content drops, and of course the toughness gets higher. So we looked at this in some detail. This is our favorite fish. This is the Arapaima fish, which is this enormous fish that's found in the North Amazon lakes. And these lakes are full of piranha, and the piranha have, of course, they're devastatingly attacking fish. But these big Arapaima seem to have survived extremely well. So we looked at this. Actually, Mark, who goes to Brazil quite a lot, got some Arapaima teeth, and we did that from the perspective of doing a hardness test. But the intriguing thing here is not that hard surface layer, it's the subsurface tougher layer. How does it generate this toughness that accommodates this massive deformation? And a lot of natural structures, and certainly Arapaima are one of them, have this Boulegan structure of the collagen. This is a spiral staircase. It's like Liberace spiral staircase. And it's not a perfect, the angular changes of these structures are not perfect, but this is this sort of spiral structure. And what happens when you put a tensile load on this, for example, you would get subsurface if you had a penetration. And we can follow this with the synchrotron in this small angle X-ray scattering. These layers of collagen tend to rotate to carry more of the load. It's what we call structural adaptive reorientation. The ones that are the long way orientated from the load, they will tend to orientate in the other direction. But most of these layers will rotate to carry more load. It's a very, very interesting toughening mechanism. And I've shown it here. This is the single Boulegan structure. And you watch a crack here, and you can see these interpenetrating layers of collagen, which have to pull apart. And there is bonding between the layers in certain fish. And this is a very, very tough structure. There's some fish that have a double Boulegan structure, which is two orthogonal spiral staircases, which this was on this famous cyst, the silicon fish that was found in Madagascar in 1938. It was thought to be extinct for 50 million years, and it still exists. So this is a sort of we call this fish a living fossil. These scales are much less flexible, but the toughening is even greater with the double Boulegan structure. Really very interesting. And if you look at just the engineering aspects here, this is an Ashby plot of the toughness versus the modulus. And these Arapaima scales are right up there. They're extremely tough. We can measure R curves and so forth, but they are very, very tough structures. So again, graded structures, hard surface, tough underlayer, but this particular Boulegan structurally adaptive structure of the substructure of that layer is a very, very tough region to accommodate that extra deformation. So what about skin? Skin is another interesting one. This is skin. Skin is just ridiculously difficult to tear. This is a tensile test on skin, and it just goes on and on and on. I won't continue it, but how does skin do this? Well, if you do a little sort of put a notch in skin and you pull it, you can never break it. It just tears and tears and tears. So we've looked at this very carefully in the dermis layer, which is the main layer we deal with skin. And what you see here is these very long and curly collagen. They're not mineral, these are purely collagenous structures. But we can follow this again in the synchrotron and see what happens. And we can watch this sort of tangled mass of collagen. And as we go to higher and higher strains, you see a sequence of events. This collagen basically sort of straightens, and then it tends to rotate until it's all aligned along the axis of the loading, not all, but most. And then you start to see separation of the collagen, and finally you see delamination. So you can see it here. This is what the collagen looks like initially. And then when you've pulled it, you've got this untangling, the curliness sort of uncurls, and then it gradually rotates. And then you've got the fibrillar sliding between the collagen. These are very effective mechanisms of absorbing energy that make this material skin very, very difficult to tear. This is rabbit skin. I think Mark got it from roadkill. I don't know, but this is what we've looked at. But you know, there's a hang glider in the States here that jumps off Half Dome in Yosemite, and he attaches his wings of his hang glider to his skin, not to a harness. And that just shows you how, if you put these hooks in the right orientation in the skin, then you can get very high strength. So let's change the subject quickly from biological materials. Biological materials, as I said, oftentimes balance is intrinsic and extrinsic, not skin, but certainly bone does and fish scales do and so forth. But another interesting material, of course, is ceramic composites and ceramics in general, but particularly these new ceramic composites that are being used in jet engines by Rolls and particularly by GE. And these are typically silicon carbide matrix with silicon carbide fiber, and they have the potential to be operated at extremely high temperatures. So we designed a rig in the synchrotron to try and look at this at temperature. This is basically a little hot cell that goes in the beamline. There's a load cell here. We can do a tensile and a bend test on it, but the sample is basically heated with 6 quartz lamps, and we can generate extreme heat here focused on a region of about half a cubic centimeter. So it's a macroscopic region, and then we pass the X-ray beam through it, and we can see in real time through the material, and we can see how the mechanisms develop. It's a very potent mechanism for looking at very high temperatures. Because how else would you do it? You'd have to cool the sample down and section it, and that, of course, all sorts of things change in those conditions. Let me just show you some of these images. This is a stress strain curve at room temperature. You can see the fiber structure. There's a toe here, there's the fibers, and there's the matrix. But we can, during the tensile test, we can see into the material. We can see how every fiber breaks. We can look at the distortion or the pull out, and we can see the bridging developing and the various different cracks at a function of load. Everything you see in that image, we can quantify with this technique. This was developed in a program with Brian Cox and David Marshall, and a lot of this was done by my postdoc, Ritchie. Now that's at room temperature, okay? But we can do this at high temperature. This is done at 1750 degrees. We can do a tensile test, and again, we can see everything in real time. I haven't broken this one open, but as we do the tensile test, you can see a crack develop. It breaks open here, but you can see the bridging of the silicon carbide fibers, which is so effective in these materials. These are woven three-dimensional ones, the ones that are used currently by GE and Pratt, and Rolls-Royce are more sort of two-dimensional layups. But the key is keeping these fibers intact, and in these structures that they use boron nitride coatings to keep the interface weak. These are also now used in nuclear structures as coatings for fuel particles. At least they're talking about that. Similar structures, but they use a pyrolytic carbon rather than boron nitride to keep the fibers being able to pull out. But you know, looking at this is the room temperature test and the high temperature test. You can see the stark differences, multiple cracks at room temperature, then the single dominant crack that then breaks out eventually. But we can look here at all the sort of details. that was looking at the fibers and where the pullout was. This image looks at the individual cracks. You can see the fibers, and these are the cracks that form, multiple cracks at room temperature, the single dominant crack at the high temperature. The color code here tells you the width of the crack. So we can measure the crack opening displacements. And this went into Brian Cox's modeling. And it's a very potent way then of doing a few coupon tests, which give you a lot of information. But you can see a stark difference in the behavior at room temperature versus high temperature. And all this is done in situ. We can see this in real time. And we can, of course, measure all sorts of things, the details here, the pull out of the fibers. We know exactly where the cracks are in relation to the main cracks, and all as a function of load and the number of fiber breaks and everything. So it's a very potent way of getting lots of information. But and we can also look actually at the environmental effects. One of the problems with the boron nitride coatings is they can degrade, and the boron can move and poison the interface with the environmental barrier coating. So we've looked at this, and these little green regions here, there's a crack again, slightly lower temperatures, down at about 1500, but we can see where the coating breaks down, and you can post SEM analysis, you can see how there's layers of silica formed and so forth. So this has a potential for looking not just at final damage, but the degradation due to the chemical effects or corrosion effects. So just quickly, we've also used this technique for looking at a graphite. This is nuclear graphite. This is work done in association with Dong Lu, who was at Oxford at that time, now in Bristol. You know, graphite's a pretty important material in the core of nuclear reactors. Used as a moderator, but there's a lot of really important components there. And the existing graphite that they were using is gilzo carbon, which really is, it's peat. It's sort of dug up in the north of England, and it's terrible material. It's got so many defects in it. There's more defects than there are material. This is a picture of the carbon. There's porosity, there's micro cracks, there's these filler particles, which are basically like onions, and these cracks form along the onion layers, which are the basal planes of the graphite. So it's terrible stuff. But we were able to do fracture toughness tests in this hot cell of mine on the Berkeley synchrotron, and see in real time what was going on. And this is a picture of, this is just DIC or DVC techniques to see what's going on in terms of bridging and so forth. But if we measure the properties here, this is the strength, and the strength actually increases as you go up in temperature. And these are R curves of the fracture toughness of graphite. The red is hot and the blue is green. And you can see as you go from room temperature to 1000 degrees C, this material gets tougher, which is pretty amazing actually, that the material so defect ridden should actually get tougher at higher temperatures. So we did a lot of work in looking at the defects, and there's defects all over the place. You can see the crack, there's deflection, it's encountering a filler particle. The filler particle then separates along the basal plane, all sorts of stuff going on. Deflection, micro cracking, bridging, really tortuously complicated cracks. But we don't think that's particularly important in this case. What we found was when we did in situ Raman spectroscopy at high temperatures, and this is Martin Kubel's rig down in Bristol University, we found that there was a lot of residual tensile stresses in the graphite at room temperature. It's cooled from a very high temperature when they process this, and we think it just freezes in these tensile stresses. And if you look at in the microscope, you can see all these little micro cracks, and they're called Moscow cracks or something, but they form along the graphite basal planes wherever they are, and they're all open at room temperature, presumably because of these very, very high residual stresses. But when you go to higher temperatures, and we're able to see this with the Raman, then these residual stresses basically relax. So now at high temperatures, the nano cracks are all closed. So we think the main mechanism responsible for this remarkable increase in the toughness of the graphite is associated with the relaxation of these local tensile stresses. Very interesting effect. So then let me finish by talking about metallic alloys, and I'll look at two which are relatively new alloys, and they're both multi-element metallic alloys. And the first of these is the metallic glasses. We work with Bill Johnson on this, and so he's pretty prominent in what we've done. But you can see this is the metallic glass, and it's pretty tough. And there's another one, and you can see the big plastic zone at the crack tip. So these materials have the potential for being remarkably tough, but they tend to form single shear bands. So a lot of glasses, as you might expect, have virtually zero ductility. As soon as you pull them, you form a shear band, it zips across the sample, and you've got a toughness in the range of 1 to 5 or something like that. So that's the curse of these metallic glasses. They have this single shear band problem. But the interesting thing is, if you can develop multiple shear bands, those shear bands are the essence of plasticity. That's how these materials deform. So the key is to get multiple shear banding and not just have single shear bands. Now these materials have plenty of strength. They're amorphous, of course. So if you can generate ductility, you can get pretty good toughness. So there's several ways you can do this. The first of these ways was the way that Doug Hoffman did when he worked with Bill Johnson, was to put in a second phase. And the second phase blocks the shear bands. And we did some of the toughness tests on this. And so you want to make certain that the spacing of these second phase doesn't allow these shear bands to get long enough that they can exceed the critical crack size. We talked about matching the microstructural size scales, which is the spacing of these arresting particles, to the mechanical size scales, which was the critical crack size. And if you do this, we got remarkably good toughness. This is fracture toughness versus crack extension. This is one of these R curves. If you take a regular zirconium-based glass, it simply breaks at 50, catastrophically like this. But these materials had pretty good R curves, and they generated extremely high toughnesses around 200 MPa root meter. And so Hoffman has been working now at NASA, and these are apparently going to be used for a lot of space components. But the other way we tried was, can we do it without putting a second phase in? Because the second phase is about 60% of the glass, and it's a crystalline phase. So this is really not an amorphous material anymore. So we tried it with a palladium glass. Now, this is obviously not going to be something that's going to be useful industrially because palladium is so expensive. But if you do a fracture toughness test on this material, it's remarkably tough, and there's this multiple shear band process here. So our sort of limited idea here was to change I think this is called the Pew ratio. If we had a low shear modulus, we get lots of shear bands, but the high bulk modulus would prevent them perhaps from opening and forming cracks. So that was our philosophy. But this particular material, it's not very, it's got a palladium, it's got silver in, it's difficult to make as a glass, it's super expensive, so it's not really practical. But we got strengths here of 2.5 gigapascals just in a tensile test. And from this fracture toughness test, we measured the toughness. We used COD techniques, and you can see it's extremely tough material. And if you looked at the R curves that we generated, we're getting toughnesses of around 200 megapascal root meters. So this is an amazing material. This is a 2.5 gigapascal tensile strength with 200 megapascal root meters toughness. So this is on an Ashby plot. This is the toughness versus the yield strength. We're right out here. We're right on one of the toughest and strongest materials you can generate. So this is amazing to me that a material that's this damage tolerant is basically a glass, which is somewhat surprising. So we got a nice paper in Nature Materials on this, and we got a lot of press. In fact, my favorite one was, we called this material a tough glass, and I got a letter from Ferrari saying, we think this would make the perfect windshield. And I said, well, it's got all the properties you want. There's just one problem. It's, of course, not transparent, so a detail. But subsequently, we looked at this material, and we did a number of tests in different sizes. We got more material from Germany. And we found that, yes, in the material, in the small samples, we got toughnesses of 200 megapascal. But when we did the same material in a larger sample, we got toughnesses of 23 megapascal meters. Now that's quite a huge variation in toughness, quite frankly. And this is not unusual for metallic glasses, but nevertheless, this is a little bit too much to deal with. So something was a little bit remiss here. So we looked at this in some detail, and this is with Jay Kruzik and Bernd Gludewatz, who Bernd was my postdoc and Jay was my former postdoc. And we plotted the fracture toughness as a function of the size of the sample, mainly the ligament size. And we found that while we were in linear elastic fracture mechanics regime, where we had, you know, a ligament that was large compared to any plastic zone, then we got pretty well uniform properties. But as soon as we got out of that regime and we got into what you would call the J regime, then we got, even though we were measuring valid J's in terms of nonlinear elastic fracture mechanics, the scatter was horrendous. It varied from, as I said, 20 to 100 to even higher. So we thought, this is what's happening here. And what we think is happening here is, as you know, when you get into nonlinear elastic fracture mechanics, the important thing is that you have an HRR zone at the crack tip, which is a power hardening zone. You need that strain hardening at the crack tip to give you some degree of uniqueness. If you go to fully plastic non-hardening fields, there's nothing unique about a bend sample versus a center crack tension in terms of the crack tip fields. And I think what we have in metallic glasses is these things don't harden. The hardening is geometric, but there's softening in the essence of the plasticity in the slip bands, and so we just don't form a unique HRR field, I think. And so the limit, so the nonlinear elastic fracture mechanics J field region in these materials is extremely limited to the point of being probably non-existent. So it's very difficult to measure the toughness when you get to the tough materials. And this is going to be a limitation if you can't characterize it. But there's another factor which is a little bit even more interesting. And that is the fact that these glasses, they're amorphous, but what does amorphous mean? Now, certain people talk about that the amorphous glasses, like Lindsay Greer, have a nanostructure. And what we've done with this, and this is something that came out of Evan Ma's work with Jun Ding, who became my postdoc, with Mark Astor here, and that is the fact that in the amorphous state, the short range order. And the short range order is little motifs of atoms, which typically have icosahedral symmetry. The five-fold symmetry makes them the most stable. But some of these motifs are less closely packed. They don't have as much five-fold symmetry. And Evan gave them this beautiful name, GUMs, which stand for geometrically unfavorable motifs. So you can find these things, and most of this has been done, you know, with DFT and MD modeling to show that they exist. But what's intriguing about these things is when you do the modeling, these GUMs, or these unstable motifs, are the things that trigger shear bands. So if you have a few of these things in the structure, you get single shear band formation, which gives you this very low ductility. But if you can get a larger distribution of these GUMs, then you can generate multiple shear banding, and you can see you generate now some degree of ductility. You can do this by changing the composition, and you can do it by things like changing the cooling rate. And it's really interesting because all the things you do to glasses to make them more ductile are exactly the opposite to what you do to a conventional material. If you anneal them, you get rid of the GUMs and you lose the plasticity, so they embrittle. If you quench them, you get lots of these GUMs, and then you get lots of shear banding, and you make them more ductile. So it's a very, very fascinating notion in this regard. However, it's all based on first principles atomistic modeling, and of course, that's not that close to reality. So what we've tried to do is, can we actually see this in real time? And this is basically working with Andy Miner, who's part of my program now at LBL, who has at the National Center for Electron Microscopy. He's been developing lots of fascinating new techniques. And one of these things is this basically 4D STEM technique, where we can do multiple diffraction patterns over very small regions of material, typically just a small collection of atoms, but we can do these very, very fast. We can do initially we're doing them at 400 frames a second. We're going up to 100,000 frames per second. So we can scan a material looking at small regions of atoms and get their structure. This is ideal for looking at short range order. We can also measure the strains there as well. So we tried to do an experiment, and this is the experiment. We put a notch in where we can generate a shear band so we can see the strains, but at the same time, we tried to look at the symmetry, the degree of icosahedral symmetry that was prevalent, representative of these gums. Now, this is not the perfect experiment, but it's the first time it's been done. If you do the thing with modeling, MD modeling, then it's fairly straightforward. This is our hole in our sample in the TEM. You can see that, of course, where the shear bands form. This is the maximum deformation, the shear. This is, and if we now look at the local icosahedral ordering. Now, remember, the gums have lower symmetry, so they would be the darker regions. The regions that have the less icosahedral symmetry, either regions of gums, coincide with where these slip bands are forming. So that's what the modeling says, and we've tried to image that with these techniques. This is not overly compelling, I must say, but you can see again this sort of where the shear bands form. We can pick that up in terms of measuring the local strains, and you can see the regions of lesser icosahedral symmetry where the gums are, and you could probably convince yourself that they do coincide with where the regions of the shear bands are. So, you know, the modeling is saying this is where the local strain forms, and this is where the fractions of these gums form. We're going to redo this experiment because the problem with this one is a notch there, and so it's a bit of a chicken and egg. If you for a shear band, you're going to mess up the local ordering anyway, and vice versa. But this was our first attempt to try and show that this fascinating effect of less icosahedral symmetric motifs of atoms in amorphous structures can trigger shear bands. That triggers the plasticity, which coupled with the high strength of these materials gives them their toughness. It's a very, very unusual mechanism. Finally, I've just got a little bit of time left to talk about high entropy alloys. These are the other multiple principal element materials. The entropy aspect is probably less important now, but these are a new class of materials. The ones we've looked at are the original ones, the so-called Cantor alloy, the 5-component chromium, manganese, iron, cobalt, nickel, and the ones just simply chromium, cobalt, nickel. These are FCC materials. They're fully single phase, unless you age them for months. They're single phase materials. And so they at least embody the original concept of the high entropy alloy. So let's look at these. This is the one that the Cantor alloy, this is the one with the 5 components. Has a nice ductile stress strain curve. It's got about a strength of 700 megapascals at room temperature. But I think, as you all know, as you go down in temperature, down to liquid nitrogen temperatures, it gets harder. Well, that's no brainer, but it also gets more ductile. In fact, we get about 70% ductility at liquid nitrogen temperatures. So this is a material that shows exceptional damage tolerance. We measured the fracture toughness in these materials, and we found that they have remarkable fracture toughness. These are JR curves. The toughnesses at liquid nitrogen temperatures are well over 200 megapascal root meters. This material has a strength of about 1.3 gigapascal, so it's an amazingly strong material. It doesn't degrade in toughness at low temperatures, and we're getting, for the crack growth toughness, which is fully ASTM valid, we're getting over 300 megapascal root meters. Now, this is due to steady strain hardening, which generates this, and it's enhanced at low temperatures because you form these nano twins. But this steady strain hardening is intriguing because you get this duality of deformation mode. You get a synergy of deformation, which provides for both strength and ductility. For example, if I look at this material, you see these planar slip bands where these ponderous undissociated dislocations move along the slip bands. This is a strengthening mechanism, but by the same token, if we look at the partial dislocations, this is again these undissociated shear slip bands, but you'll see a partial dislocation move in here very, very fast. And so there's a rapid motion. There you see, there the partial came in. There's a rapid motion of partial dislocation. So this provides for strength, this provides for ductility, and then you add the twinning at low temperatures and you get remarkable strain hardening. Strain hardening is great because it increases the hardness, but it delays necking. So you beat the strength toughness conflict. You also see bridging in these materials. They're kind of interesting, these little bridges, but this is probably an artifact of the thin film in the TEM. Just briefly, we've looked at a simpler one. This is the 3 component, which is simply cobalt, chrome, nickel, and this is even tougher. Now we're at liquid nitrogen temperatures, the material is strengthened and toughened. We're getting 1.3 gigapascal strength. We're getting 90% tensile ductility, and the fracture toughness tests are giving us numbers like 273 megapascal meters. These are mind-boggling toughnesses, and in fact, the crack growth toughness is over 400 megapascal meters. We think this is the toughest material to date. Again, this one is stronger, so twins more readily. So it's a heavily twinned microstructure, even at room temperatures. And you again see this duality of deformation. The twin boundaries can act as barriers to arrest dislocations. This is the strengthening mechanism. But by the same token, we see massive cross slip coming off these boundaries, which provides for ductility. And we see the actual twin boundaries themselves act as pathways for dislocation motion. Again, duality of deformation. These provide strength, these provide ductility. So these alloys, this is again an Ashby plot of toughness versus strength. This is these high entropy alloys. They're right up there. We think they're the toughest materials out there. They don't quite have the strength of the glasses, but they're certainly extraordinarily tough. We've done, this is, by the way, some of the microscopy done by Yu Chien at Zhejiang University, who used to be a student at Berkeley. Very nice microscopy. So we've done microscopy, well, she did microscopy at liquid nitrogen temperatures or near liquid nitrogen temperatures at 93K. And you see these mechanisms operate at these very low temperatures. You see the formation of twins and then secondary twins. We see these massive cross slip coming off the slip bands. And you see all these arrest modes where you get pileups against twin boundaries and grain boundaries, but it'll still generate twins and dislocations. So again, you've got these mechanisms that promote strength and that promote ductility. Just one more movie here shows the, this is at near liquid nitrogen temperatures, and you can see the twin boundaries, which do arrest dislocations and impinge on them, also provide pathways for these dislocations to move. So I'm running out of time here, so let me just gloss over a couple of things and just end with one point here. These materials have exceptional toughness, strength, and ductility, remarkable. And these properties have all been attributed to things like high entropy. People talk about sluggish diffusion. They certainly have a lot of lattice distortion because they have multiple elements in. And these generally refer to the randomness of the solid solutions. But one of the questions we've asked is there anything special about these materials? Is there any unconventional atomic structures? Is there any local ordering with all these elements? And this is a bit of a controversial topic, but we've looked at this, and let me just end with this. We did, most of the work for this has come out of MD, but more importantly, DFT modeling. And when you do DFT modeling, we did this is Jun Ding's work with Mark Astor, who's looked at this. We find that by putting in short range order in these structures, we get dramatic changes in things like the stacking fault energy. As you raise the degree of local order, this is in a model, of course, then the stacking fault energy moves from minus 43 millijoules per meter squared to 30. Massive changes in stacking fault energy. This is done for the 3-component system. We also find differences in the hexagonal to face center cubic phase. Some of these materials trip. They'll trip from a FCC to a BCC structure, and this all seems consistent. We found that it affects the dislocation mobility and the slip mode. So there's a lot of work here that suggests that local order is important. So the question is that local order there? Because this is modeling, right? And as I said, DFT and certainly MD have ridiculously, and MD has strain rates of a nuclear bomb. So these are not close to reality. So we've asked ourselves 2 questions. Can you actually see short range order? Can you actually detect it? And if it's there, does it have an effect like the modeling would suggest? So two experiments that I'll do quickly. One was with the UGN, which was looking at the counteralloy, this 5-component system, and then the one where we've added palladium, which is a much bigger and has a change in electronegativity. So all these elements are sort of similar on the periodic table, and to look what's going on. And we do this basically EDS atomic resolution, and we can look at the variations of elements. So in for example, this 5-component system, each element should be at about 20%. And when you scan across the structure, you're looking at columns of elements at a very small scale. We can see that they have a randomness about them. There's nothing particularly special about this, but when you add the palladium atom, you get this large variations in structure, which are periodic. We can't actually characterize clusters here, but we talk about concentration waves here with a scale, a wavelength of about 3 nanometers. That's much greater than normal short range order. But then you can look at how this affects the local strains at the atomic level. And you see, this is measuring the strains in the counteralloy with the elements that are pretty uniform. Then it's not much change, but when you put the palladium atom in, you get a lot of change in local strains. And all the elements show variations, not just the palladium. So this is notion of the roughening of the lattice, which could lead to hardening. This is what we basically tried to suggest. We did a second experiment. This is with Andy Miner at Berkeley, was to try and measure short range order directly. We use an in-column energy filter, which gets rid of the inelastic scattering of the atoms. And we looked at a water quench sample, which we hope was random, and one that we annealed at about 1,000 degrees to give us the short range order. And when you look at the diffraction patterns, you can see streaking here, which is indicative of superlattices. The details are kind of difficult to go through because this can be interpreted in many different ways, but there's a paper in Nature that came out earlier this year, which I think describes this pretty well. But we can identify domains of atoms here, little domains on about the one nanometer scale, which we would interpret as clusters. We can also see preferential bonding. Chromium likes to bond in this 3-component system with an unlike atom rather than a like atom. So we think this is a reasonably good proof that the short range order does exist. That's question number one. The question number two is it relevant to the mechanical properties as the modeling would suggest? Well, we do see a change in slip mode. In the random solutions with quenched, we see wavy slip. We tend to see planar slip in the age structures, and nothing's changed here. It's all single phase and so forth, which is indicative of the presence of short range order. Directly correlating to what we saw with the DFT, we see much larger spacings of the partial dislocation in the random structure, indicative of a lower stacking point energy. When we have short range order, it raises the stacking point energy, and that's completely consistent with what has been seen by the modeling. And when we did mechanical properties, we do see elevations of strength and hardening, and we see even changes in the modulus. Now, the problem with this is that these samples are all very small, and so we need to do this in thicker samples. And what worries us here is that we can quench this thin sample to generate what we think is a random structure, but can we do this in a thicker sample? I.e., does short range order always exist? So we've been in discussion with Bill Curtin here. He thinks that he can predict these strengths just on basic dislocation type models, so that the effect of short range order, even though it's there, may not be relevant. It may not have that big an effect. Our initial experiments suggest that it will have a big effect, but the jury's still out on this one. So this is an interesting aspect. The fact that short range order exists in these alloys, we find fascinating, but the relevance of that in terms of what it's going to do to mechanical properties, we think there's an effect, but again, this has not been overly proven. And these alloys, nevertheless, are extraordinarily tough, as are the glasses, but these high-energy alloys are even tougher. So let me conclude. I've talked about the various mechanisms of of toughness in materials, be them intrinsic based on plasticity, extrinsic based on shielding. The intrinsic mechanisms play a role in the metallic materials. This is where the conflict of strength and toughness comes from, because you need plasticity to generate the toughness. The high entropy alloys are really the classic example of that, by generating mechanisms which promote ductility and promote strength in terms of dislocations and generation motion, and generating these steady continuous strain hardening. The glasses are something very different, but they're certainly very interesting. The extrinsic mechanisms are, of course, largely in the range of brittle materials like ceramics. It's shielding, particularly deflection and bridging. Ceramics do that very effectively. And then I think biological materials have this ability to generate both these mechanisms, I believe, because they have this multitude of length scales, hierarchical structures, which enable to tap in at different dimensions of length scale to generate these various measurements of various mechanisms of toughening. Thank you very much.
Great. Rob, can we ask you to unshare your screen? All right, Nanshu, please go ahead.
All right. Come on. Thank Rob for a blast of nice images, videos, and all the physical insights of fracture of a variety of materials. Thank you, Rob. It's really mind-blowing. One logistic announcement. Currently, we have 21 panelists and 129 attendees. So for attendees, if you want to ask a question, please click the hand button at the bottom of your screen so that we can promote you to be a panelist. And as a panelist, if you want to ask a question, please click participants. And there is going to be a white window pop up. And please click raise hand at the lower right of the white window so that we can see a blue hand. All right, now we have a few hands already raised. Professor Franz Spappen.
Hello, great to see you, Rob. Great talk, as always.
Thank you very much.
Quick question. On the metallic glass, you care to comment on these rejuvenation experiments where you fill up the material by constrained plastic deformation? And what do you expect there in terms of toughness? These are still small samples and all that, but have you had a chance to look at some of them, and what do you expect there?
That's a fascinating question. I mean, the rejuvenation, we think, is just a means, possibly a means of developing a new range of gums there. But we've tried to. We've been trying to do this experiment where we want to take a material and we want to change it macroscopically, like annealing it or rejuvenating it, and measure a change in the ductility, and then do the same experiment in the microscope where we can actually see, hopefully, a larger proportion of gums, and we can relate those to the shear bands. And of course, the modeling would show the same thing. So that's the experiment we've been trying to do. The problem is we can never get rejuvenation to work. We've tried several times, and admittedly, one of the problems is to be able to do the MD modeling, you need to have a simple structure. You need to have a 2 or 3 component glass, and they're brittle as hell, so it's difficult to see a change in ductility. But we have never got rejuvenation to work. And so, you put it in liquid nitrogen, you pull it out, put it in liquid nitrogen, pull it out, but we just not got it to work. So
I'm thinking of doing it mechanically. That is the way Lindsay Greer and his collaborators have been doing it. You just put it through a lot of constrained plastic deformation so that shear bands can't ruin you, and just fill it up with plastic deformation. And
yeah, well, maybe we should try that. But
yeah,
I mean,
try that. Yeah, get some material from Lindsay and give it a shot, because I'm curious to see if you do.
What we'd really like to see is just how we'd like to see a gum trigger a shear band if we ever can. I think the experiment I described what you just said is that if you can do something macroscopically to the material and measure those properties, a change in ductility, for example, and then then see that in terms of an elevation and shear band formation or the gums in the microscope. I think that would be the experiment. We will try that, because I think this rejuvenation is fascinating, but we've tried it 3 times, but using the thermal route. And
I think the mechanical one is much more direct, and it's probably easier to do.
Well, I thank you for the advice. We'll try that, definitely, yes.
Okay, thanks, friends. Next, Mattia Baca.
Hello, everyone. Thank you, Professor Ritchie, for this beautiful talk. I have a question in regard to the intrinsic toughness. And I was wondering if damage and stiffness degradation in material, especially biological materials, biological polymers, can play a role on intrinsic toughness.
So I didn't quite catch that, sorry.
So I was wondering if damage and stiffness degradation can play a role in intrinsic toughness.
Well, I'm sure it can. I mean, these are not unique modes. It's a way of classifying them because they have certain different aspects. But if you're dealing with certainly a material that's bridged, and you see a reduction in the stiffness, you can associate that with breaking of fibers or something like that. So that certainly could be an intrinsic portion. So I think that's perfectly reasonable. But I don't know so much about polymers, but crazing in polymers and things like that, how you classify those in terms of intrinsic and extrinsic are a little bit more difficult to do. I like to think that if it's ahead of the crack tip and you're restraining that damage, that's an intrinsic process. The extrinsic ones are generally more associated with a shielding process. So I think there's a component of both in what you're talking about. So a change in stiffness of a polymer associated with a crazing phenomenon or a breaking of a fiber thing can have an extrinsic and an intrinsic component to it. It's just that the extrinsic mechanisms need a crack, so they have no effect on crack initiation. They only affect crack growth. They will immediately generate an R curve. But of course, plasticity in the wake of a pure intrinsic metal is a means that by which an R curve is generated. So there's an extrinsic component to that too. So it's a little difficult in some of these situations to classify, but I think I like to separate those two processes because they have distinct differences in terms of the effect. One is, they both can generate R curves, but one is you have to have a crack there, and the other one is a damage process which leads to a crack. So a little difficult to answer that question precisely though.
All right, thanks, Rob. Next, Masato Koizumi. Please introduce where you are from.
Yes, first of all, thank you, Dr. Ritchie, for your wonderful talk. My name is Masato Koizumi. I'm from UCLA. I work under Professor Li Huajin. So I actually do fracture. My research is on computational mechanics. I do a lot of work with fracture. And I had a question regarding your R curves, which you plotted for your alloys. How do you ensure that there is no unloading when you actually plot your R curves? Because when you plot your R curves, you were plotting the J integral with respect to the crack extension. How do you ensure that there is no unloading when you actually plot the J integral for each as a crack?
We follow the ASTM standard for this, and there's a 1820, and we use periodic unloading by about 10% to give us a measure of the crack size. We use a backface strain gauge on the sample, and then as we go along the load displacement curve, we will unload it by about 10%, measure the unloading compliance, which gives us a measure of crack size. It's a completely, it's the ASTM method. At least it's part of the standard. I'm not quite certain the basis of your question, but one of the problems there is, though, is that when you're in linear elastic fracture mechanics and looking at crack initiation, you're in a very robust form of fracture mechanics. But as I think Joe Gallagher once said, if you can fully characterize a material in terms of K1C, you probably don't want to be using it because it's by definition doesn't have much plasticity in it. So from a material scientist point of view, you want to be materials where you can get out on the R curve, But once you're on the R curve, you have the point you're talking about. As the crack grows, there's a region of unloading as the crack grows, and there's a region of proportional loading there as well. That's what I call a zone of violation. It's like a plastic zone in a linear elastic test. And so that zone has to remain small in order not to justify a J integral approach to characterizing the stresses. And that's what the ASTM standard tends to do. And so if you looked at my R curves for the high entropy alloys, there is a certain dotted line after a certain maximum crack size. And that's when the standard says you've run out of steam. You've got too much unloading, too large an unloading zone or too large a proportional zone that you can't ignore it anymore, right? Just like you can ignore a plastic zone if it's small enough. So that limits the validity of the ASTM test. So we will quote two numbers. The initiation toughness is the crack is not grown yet. So that's a pretty hard and fast number. And with these high strength materials, we satisfy all the J criteria and so forth. But you can move out along the R curve again, and you are satisfying ASTM criterion for a J controlled growth, because you don't have the proportional, non-proportional loading zone is still relatively small. But at some point, there's a maximum value when you don't do that. And we stop at that point. And that's the number I give for a crack growth toughness, because that represents a ASTM valid toughness for the growth of the crack. So that's so we try to be, I mean, as Franz will know, in metallic glasses, I think that something like 60 to 70% of all the fracture toughness tests on metallic glasses are wrong. They've all been, they violate every ASTM rule under the sun. But we try to be very careful in that regard. With biological materials, it's a bit more difficult, but we try to keep true to the notion of fracture mechanics, in that you're characterizing the stresses and strains at the crack tip in terms of a characterizing parameter, be it K or J or C star or what have you. There are regions at the crack tip which violate these assumptions, like a plastic zone in linear elasticity, an unloading and a non-proportional zone in non-linear elastic fracture mechanics. And those zones have to be small enough relative to the dimensions of your sample that you can ignore them, basically. And that's what the ASTM standards try to do. And that's what we try to adhere to. I mean, but a lot of this has been forgotten now amongst the material science community. I mean, a lot of the toughness data you see measured in the material science community is just, it's at worst wrong, and at best crack size and geometry dependent. But at least we do try to adhere to those rules.
I see. Can I ask one more question?
Yeah, sure.
Looking at your R curve for the bone, why does the R curve diverge instead of actually reaching some saturation point? Your R curves for the bone seem to actually diverge or keep on increasing.
Yeah, well, I mean, you have to ignore that. I mean, that's I mean, you don't measure the toughness there, but in a small sample and with a bone, you have a finite size sample. It's the size of the bone. You can't go any bigger. If at some point then the crack becomes too long, and to satisfy the conditions I've just said. And so you'll get a concave up type R curve. And as soon as you see that, you know you run out of steam. I think David Clark talked about large scale bridging in ceramics that do that. And I've been quite critical of people who've tested bio-inspired materials in too small samples where the R curve has started to go concave up, and they've quoted that as a toughness. That's a good indication that you run out of steam with the sample. So we, in a lot of the papers we do, we sort of we set a stop when we start to see concave upwards, and we take the measurement at that point and don't and ignore all further measurements, because that's a sort of a characteristic indication that you run out of steam with the size of your sample. It is particularly a problem in biological samples because they are the size they are. So, but this is, I think, the problem with fracture mechanics is that it's robust where you don't need it so much in terms of, you know, but when you get to materials where you want to generate this R curve, I mean, an R curve, a rising R curve to me is as essential as tensile ductility. It's what you have to have in a structural material. but you know, you are on less stable ground in terms of fraction mechanics characterization at that point. So, and some people throw total caution to the wind here. So we try to adhere to the rules, because otherwise the whole notion of what you're doing with a fraction mechanics characterization becomes silly. You're assuming there's a certain stress field and strain field there, and if you violated these size requirements, there isn't. So therein lies the problem, but we do try.
Thank you.
Thanks, Rob. You are really giving us a very detailed tutorial, especially for our young scholars. Thank you. So next, Professor Nitin Pachter.
Hi, Rob. Great talk.
How are you doing? Good to see you.
Good to see you. A great talk. As Nanshu said, it was mind-blowing. I think she put it correctly. Quick question about your biological materials. What is the role of wetness? All biological materials in nature are, of course, wet. And does it play a big role when you dry the sample or not, and so on?
That's so important. I mean, the degree humidity is absolutely critical to these materials. And if you test them dry, you're testing a different material totally. I mean, there's a lot of people who've done work on bone in vacuum, and of course that's really an irrelevant scenario, because bone doesn't behave that way, and it's not. I remember listening to a talk where someone was working on bone in hydrofluoric acid. I thought, well, why the hell would you ever work on that? What possible relevance would that have, unless you were an undertaker or something? But it has a big effect. But it's intriguing. I mean, water acts like a plasticizer in a lot of biological materials, and so it induces ductility. And when you put it in vacuum, for example, if you look at dentin in teeth, the toughness of dentin in vacuum is just near zero. It's just not the same material. You add the water, and I think you form hydrogen bonds, and it becomes plastic, and you break those, you form plasticity. If you even put any fluid in, even if you put acetone in or alcohol, you'll still get an effect, which is intriguing. So, but I don't know enough about the poroelasticity of some of these. I mean, dentin has something like 40% fluid in it, and so that's clearly very, very important to the mechanics of how that material behaves. I don't know enough about that, but it's an absolutely vital thing. So if you're testing biological materials, you have to test them wet. We do a lot of in situ SEM work, and we've gone to an environmental microscope where we can basically keep the sample relatively moist. They're all sort of saturated in some kind of blood analog solution or whatever for 24 hours before. In the tomography, we wrap the thing in a towel, you know, a wet towel to do things. But I try to do tomography of bone in real time, rather than looking at after I've tested it in water in a testing machine. I try to do in situ experiments with bone in the microscope. And of course, we got completely different behavior because we couldn't keep it moist. And the other thing is, of course, the irradiation damage is dramatic for things like tomography. I mean, you're putting on several megagrays, and effectively you lose most of the strength of bone after half a megagray, or even much smaller than that. So there's all these issues. So there are people who do a lot of tomography in bone in real time, and I think those results are completely irrelevant because they're not wet and they've got this massive radiation damage. So that's a very, very important point.
Thank you.
Thanks, Nitin. Next, Professor Simo Basaret.
Thank you so much, Professor Ritchie, for an amazing presentation.
You're very kind, thank you.
When you were presenting about the bones, you emphasized the cross-linking plasticity. So if you are going to model a bone at the continuum level to analyze the whole system, would you analyze it as a short fiber reinforced composite, or how would you model it?
Well, that's not really the question you should ask me, but the reality is that the collagen is a kind of a short fiber type situation, and it does stretch, and then it slides apart. You can see that in real time, and so as the bone, if it's diseased or if it has, it's aged, the ability for it to stretch is probably not changed too much, but the ability for it to slide will change dramatically. And I think our in situ Sachs work shows that. And so I think that's a real effect. Precisely how you do the mechanics modeling, you should ask a mechanics modeler rather than me. But by the way, there's another tie-up now with bone that's very important. Is it's not just the this cross-linking thing, but it's also associated with having diabetic bone. So diabetic bone, we've done a little bit of work on that, and that is much more heavily cross-linked too. So the obesity, which is a problem with bone, coupled with diabetics, has become quite a topic. So, and a lot of this is associated with the inability of the bone to show plasticity. And I think this, we feel this is associated with the cross-linking of the collagen. So again, that doesn't really answer your question, but I'm not the ideal person to ask this question of it. But I think that's the reality. You do have collagen fibrils and they stretch, and then after a while they start to slide apart. And how you model that, if it's a short fiber model, then that would seem quite appropriate. But there is a built-in, this cross-linking, particularly this number of cross-links, but these glycation end products are the ones that seem to be the most important. There's one silver lining with this though, is how do you predict if you're going to have problems with your bone? Now, what they do now, they do these x-rays, I think it's called Dexter, and they tell you basically the bone mass. But that's not that's the quantity of the bone, but that's not really a particularly good indicator necessarily for what's going to happen. You really want something of the quality of the bone. So what do? Now, Paul Hansmer at Santa Barbara has developed this, basically a hardness indentation test that you do on a live person. But the other way of doing it would be to look at the cross-linking density. You take a small sample of bone and see if it's heavily cross-linked, then that would be an indicator that the plasticity and the potential for fracture might be increased. So there is some use in that. But again, I don't think I answered your question, but that's...
No, you did.
Yeah.
Actually, you did answer my question. Thank you so much.
Thank you, Sima. Next, Flavia Libonati. Please,
Hi there.
can you unmute yourself, Flavia?
Yeah.
Yeah.
Okay, can you
Go
hear
ahead.
me? Okay.
Introduce, where are you from?
Okay, thank you. Thank you, Robert, for your really incredible talk. So my name is Flavia Libonati. I'm an associate professor at the University of Genoa in Italy. Actually, my question is connected to the previous question and is about aging in bone. So we know that molecular mechanisms behind aging are still poorly understood. So we know about, in clinical routine, we can measure with DEXA, we can measure BMD and TBS, so we have an indication of the bone mass. We know about the alteration in the skeletal architecture, but we don't know what happens at smaller scale. So how can we unravel such mechanisms? Molecular dynamic simulation probably are the best option, but how can we directly validate them?
Yeah, well, that's a pretty good question, actually. Again, I don't have an immediate answer. I mean, the only things that we've been able to do is to measure the effects of these things. For example, what is the cross-linking and so forth, and try to identify where the engineering factors are. So I'm not you're asking a question that you should ask a biologist or rather than me. I look at the engineering sides of this, and as you do to some extent, of course, but I think that's, to me, intriguing that there's a lot of these diseases and things like aging, there is a simple engineering sequence that we can identify, but what is not obvious and what I don't have sufficient knowledge to understand is the biological origins of this. I do think some of the work that's looked at, that's looking at what happens to the various cells in bone, whether we're talking about the osteocytes or the normal cells, and how that can affect the quality versus the quantity of the bone. That's quite interesting. I know this work of Tamara Alston, where she's looked at the different cells that can be responsible. So I think that's a very intriguing aspect. But again, I'm not the person to answer the biological sides of these sort of issues, other than to do the measurements. So I've been more concerned. What fascinated me with the bisphosphonates is the fact that these fractures were so smooth. They tend to be very flat fractures, and so this to me was an indication that somehow the deflection that you normally see in healthy bone was being basically restricted. And we did a lot of studies with people like David Burr, where we looked at dog bone, where dogs have been treated to, beagles basically have been treated to high dosages of bisphosphonates, and we could never reproduce those fractures. And it was very disheartening. And then it suddenly dawned on us that, you know, the proportion of people that study, that are influenced by these abnormal femoral fractures from bisphosphonates is only, I think it's some fraction of a % of the population that take these drugs. But they have such a horrible effect that it's been so publicized that it's caused a diminishing use of bisphosphonates to some degree. But the fact is, when you've got less than a % of the population that's susceptible to this, when I look at 15 dogs, the chances of me finding that less than 1% was very small. So in the end, we looked at biopsies of people who actually suffered these fractures, and you do see the lack of deflection. So that was, and we did see this increase in the cross-linking. But again, the biological source of that is beyond me. It's not really I don't have enough biology in me to be able to answer that question. Maybe you can answer. Well, what do you think in that regard?
Yeah, what I think is that we really need molecular dynamics simulation, because we can address, we can expose this length scale that we cannot sometimes address with experiments. And we can systematically study, for instance, the effect of the cross-links or the effect of carbonate on hydroxyapatite, the effect of the crystal size. So we can get insights on the effect of this mechanism. But then, of course, there is still, it's tricky, how can we directly validate? So I spoke with biologists, and actually you can perform some experiments, but still at a larger scale. So you can perform 3-point bending on mice, but then some biologists are concerned about the direct comparison between a human, like an aged human or an aged mice, or the difference in the structure. Or you can also measure the effect of the cross-links in the collagen. So there are many experiments, but it's not a direct comparison. Rather, you can use this kind of simulation to elucidate some mechanism that you can observe then at larger scale. So that's my vision.
Yeah, that's great. But the problem with MD is, do you have good atomic potentials for this? I mean, and you're dealing with very, very high strain rates with MD, right? In comparison. And you're looking at what, cubic picometers or something like that. So there's quite a lot of problem, I think, with that at times. With anyway, I think it's certainly. I mean, I've started to use MD for these. I don't do it myself, but for these high entropy alloys. But I think it tells you something. But you've got to be very careful, I think, because it's not so close to reality as we'd like. So, but. That's what you're doing now, is it? So that's
also, yeah, I used to do in the past, but I'm also doing right now. Yeah.
I'd like to see that work when you get it out. That'd be good.
Okay. I'm trying to work on that.
Okay, great. I see many patient hands, but Nima Raba has to leave soon. So let Nima ask.
That's very nice of you. Thank you. Hi, Rob. This is Nima Raba from WPI.
Hi, Nima. How you doing?
Excellent. And it was a fantastic talk, as always. I was fascinated, Rob, by the latest part of the work, the high entropy alloys. So I am trying to go back to my statistical mechanics sort of trainings. And you were saying that these materials are amorphous, but you see some sort of a short range.
No, hang on. The glasses were amorphous. The high entropy alloys aren't amorphous. They're fully crystalline.
Oh, the high entropy are not. So that was my thinking. There's some sort of, must be a range of structures that create this. So the low order that you were talking about.
They are, as far as, I mean, the original idea was that if you put enough elements in there, you can get masses of configurational entropy, which overwhelms the enthalpy of phase formation. And so you end up with a single phase. And if that had been true, then we'd have a good rationale for trying to find the next greatest alloys, because you could just look for single phase materials. But it turns out that's not the case. The ones that Brian Cantor, the Cantor alloy, which came out that when I looked at, that is a true single phase material, unless you anneal it for a couple of months. But most of the other alloys that are out there are multiple, not necessarily single phase. There are two basic attempts now going on. There's the original face-centered cubic structure, the chromium, cobalt, nickel ones that we worked on, and they show excellent toughness properties. There's no question about it. They show, particularly at cryogenic temperatures, so they have very good strain rate properties as well. So we're looking now at very high strain rates, extreme strain rates, and we're finding very interesting things, because that's like going to low temperatures. So those alloys, those alloys are basically expensive, because they got chromium, cobalt, and so forth in them, but they do have remarkable properties. The other attempt is to go to primarily BCC materials, which have got refractory metals in. They're sometimes called RHEAs, refractory high entropy alloys. And the attempt there is to generate the next generation of a super alloy that's going to operate at 1200 degrees centigrade or something like that. And that's been less successful. There's lots of different alloys, and they have all sorts of horrible refractory elements in there. People like Oleg Senkov at Wright-Patterson's done an incredible job in mapping these things out. But basically, as you'd imagine, you're living with either great ductility at low temperatures and no high temperature strength, or high temperature strength and no ductility at low temperatures. So this is like a replay of the 1980s and 1990s intermetallics game. And so not a lot came out of that, but I think that's the other thrust now, but it's very difficult. So the alloys that look better than super alloys generally have no ductility, and so that's the issue we're dealing with. But if you look at high entropy alloys as a whole, a lot of these materials don't have that great of properties, but some of them do, and the cobalt, chrome, nickel have remarkable properties. And so, and I think what's driving the field is the great unknown. Maybe there is a new alloy out there, but the
question I want to ask you quickly was, is it possible to have that very short range in sort of a hierarchical sense? Same range in maybe a micron level, and
that's an extremely.
You see what I'm saying? So you can kick another level. Sorry, go ahead.
I know you get to microns, but I mean, unless you form a different phase, something like that. But certainly the short range order, in most people understand, has a sort of a half a nanometer length scale, and that's what we're seeing with the work with Andy Miner on the energy corrected TEM. But the stuff that I showed earlier with these concentration waves, that's a little bit coarser scale, which is you're up around 10 nanometers and so forth. And there may be other scales that we don't know. So it's very difficult to see this stuff, but I doubt if there's a hierarchical structure, but there's certainly.
No, I was just saying designing an alloy this way.
Well, we think that's it. We think that that if you could tailor the structure to generate short range order, you could generate properties. That's what the sort of story I've told before. But again, the jury's still out. We really don't know whether we can actually do that in a real thick sample, whether we can actually suppress short range order. We can in a thin sample. Maybe it's always present. That's the issue. But there's lots of intriguing issues. For example, when you have short range order, you get initially planar slip. But as soon as the dislocation moves, it basically destroys that order. So there's all sorts of intriguing issues.
That's right.
That can happen. Whether they have any relevance to properties that's significant, I know Bill Curtin doesn't think so, but we're looking in that. So, but I think there's a lot of intriguing scientific issues with these materials.
Absolutely.
They are different animals than what we've seen before, there's no question.
Absolutely. Excellent, thank you.
Thanks. Next, Robin.
Hi, can you hear me? I think you can.
Yes, I can. Yes.
Hi, Dr. Ritchie. Nice to meet you. This is Robin Bai. I currently work with Professor Kaushik Bhattacharya at Caltech, and I did my PhD with Zhigang Su a few years ago on fatigue of hydrogels. So I have quite a few questions, but I'm gonna pick one of them. So we studied hydrogels and fatigue fracture a few years ago to date. And then I came across a lot of your papers on biological materials. I read them. I even cite many of them in my presentations. So then I think I found one difficulty I found when I was reading and compared them to my study was sometimes it was quite hard for me in a polymer network or system to differentiate intrinsic and extrinsic toughening mechanisms. Because when I was thinking about that through, I found, oh, they are really in a synergistic way of toughening. I think that also happens a lot in biological systems. So, and also then another point is sometimes when you want to design these materials as a composite, let's say in that way, then it's not, you put more, say you put more concentration of this, then it's getting better. Maybe it's usually it's in the range where you optimize the property. So could you shed some light on this synergy of different mechanisms, especially when you try to design them, or even when you try to characterize them? How do you tell them differently from one batch of experimental data, let's say?
Well, this is a very, that's an excellent question. There's no question about that. The thing that's intriguing, I mean, I'll admit that in certain systems, it's difficult to separate intrinsic from extrinsic. Intrinsic is that if you think of it just ahead of the crack tip and behind the crack tip, it makes it somewhat simpler, and the metal versus ceramic is a good extreme. And you get to things like polymers, it's a little bit more complicated. So there is that. But the thing that's intriguing here is that the factors, and I don't know so much about polymers as probably you do, or certainly as you do, but I'm generally, I've tried to avoid polymers all my life. Actually, I have not been so successful, but I've tried. One of the issues is that the metallurgical factors or the material science factors that affect intrinsic properties are completely different to the metallurgical factors that affect extrinsic properties. And that's why I tried to push this concept, because, for example, if you refine the grain size for fatigue, that is good for fatigue strength generally, but it's terrible for crack growth when you've got an extrinsic effect, because you've got roughness induced crack closure. So the irony, so you get completely different effects. If you change the yield strength, it will affect the intrinsic versus extrinsic mechanisms in a different fashion. So therein lies the rub. I remember when they used to have these DARPA meetings that Tony Evans used to run down in, they had a meeting once, I remember going, this is years ago, and they were talking about what are the criteria for increasing the strength, and everybody came, you do this, you define the grain size and so forth, perfect list of chopping lists. The following year, they did it for toughness, and no one could agree on anything because it's a compromise, it's a competition between these two mechanisms, and the things that affect those mechanisms are quite different whether you're ahead of or behind the crack tips. That's why I think it's interesting, and that's why it gets difficult in your situations where you've got difficult to classify what these mechanisms are. But that's the motivation for this, and I think, you know, if you and I were designing something like a turbine, right, or and I decided to use a fraction mechanics approach, and you decided to use a stress life or strain life, we would probably choose a different material, because you know, what would give us, so you have to look at a real application and say, what is controlling life here? Is it the crack growth stage, or is it the crack initiation stage? And in many, many cases, it's the crack initiation stage. So these extrinsic mechanisms are not so important, but in many cases it is. So therein lies the issue. You've always got the intrinsic mechanisms. They're an inherent aspect of the material. You don't always have the extrinsic mechanisms. That's the problem. In fatigue, for example, it's wedging, right? So if you're at low mean stresses, you always have the wedging, and you get all these very strong crack closure effects, which have a very dominant effect on fatigue crack growth properties. But if you're at high mean stresses, those mechanisms are irrelevant, and so all that disappears. And so that's why I think this distinction between intrinsic and extrinsic is important, because the extrinsic mechanisms are a function of the geometry and the conditions. They're not really an intrinsic property of the material. I've not looked enough at polymers to try to make that distinction, but in terms of what you're talking about, I think you can do it, but I said I haven't looked at it enough. But I think there's an important difference in the significance of these mechanisms in terms of whether they apply or not.
Thank you.
Great. Next, Ahmed Albana.
Hello, Rob. Good.
Hi, how you doing?
Good, thank you. Good to see you again. Another amazing talk after your talks at UIUC a couple of years ago. So it's always impressive. I have several questions, but I will pick one, and I would like to pick your brain on the topic of mechanics and evolution. So we are fascinated by nature, for example, right? And we probably are looking at nature at the current snapshot of time, but nature has evolved over millions of years, and its predators also have evolved. And I wonder if somebody has done this systematic study to look at how the structure has evolved over these millions of years and mechanical properties it changes. Because if we would like to look at nature, at what would be the optimal materials, millions of years or thousands of years down the road, what should it be? So
that's a very good question. It's very difficult to do, though, right? I mean, if you look at biological materials that are old, then you have to worry about it. Are the changes with that material to today's materials associated with geological effects, or are they due to biological effects? I looked at dinosaur bone years ago, and I never really I could never make that distinction. So, but I've gotten into trouble recently. I did some work with Mark Myers on these Arapaima scales, and Mark is Mexican, Brazilian, so he goes back to Brazil a lot, and he swims in these rivers and so forth. And he brought back these piranha tooth, and everybody says it's amazing how these Arapaima fish have survived for eons, being able to survive piranha attacks. And because apparently if they lose a scale, the piranha will get them immediately, basically. And so we, in our papers, sort of said that, the development of the Arapaima scales has been predicated by the notion of protection against the piranhas, which is what you're saying is development. Yeah. It turns out that we've been attacked brutally by a bunch of biologists who say that that the Arapaima existed before the piranhas, and so we can't make that statement. So this is a very difficult question to ask, quite frankly. So, and again, you're asking the wrong person here, but we've come under attack for that because we've glibly said that these scales have been developed over time to prevent piranha attacks. But in terms of the biologists, they don't necessarily agree with that. But I think going back and looking at fossil type situations of fossil bone and so forth is very difficult, because you can see some of the issues that you can still see the composition of the bone and so forth, but the biological stuff disappeared a long time ago and is changed by geology. So you don't really know what's geological and what's biological. So fascinating thought though, right? Because things obviously have evolved.
And I mean, people are increasingly interested, for example, in the recent years in mantis shrimp, right? And mantis shrimp attack the mother pearl and stuff like this, right? So these pairs of arm races, as you mentioned also in your paper, right? So it's interesting.
Yeah, I think that is an intriguing thing. What we've looked at is something of a simpler problem. This is with David Casalis down at Riverside and now Irvine. Is there any sort of biological motifs that are common in different species? If you're interested in impact resistance, does nature always do it the same way in different species, or do they use different? So that's a somewhat easier one to look at, convergent evolution. But to look back in time to really sort of investigate that in a sense that you can make something definitive conclusions is quite difficult. I thought it was going to be so great with dinosaur bone, and we really got nowhere with it, quite frankly. So that was the problem, because we didn't really know what we were looking at, whether it was biological or geological. Good question, though.
Thank you.
Thanks. Next, Lily Liu.
Hello, thank you, Nanshu. Hey, Rob, it's Dawn
Lily, how
from
you doing?
University Bristol. Yes, I'm good. It's nice to see that you included our work on nuclear graphite, and you presented it very well.
Well, I appreciate the check you sent me to do that.
Well, I can see that you got questions for a lot of other areas, but you know, my interest in nuclear and aerospace. What's your view on this type of high temperature testing? Yes, we've done quite a lot over the years, but you know that is quite difficult because we need a synchrotron beamline and the samples are relatively small. So what do you think this is something actually important that we should, you know, could put more effort in, or you think that we could try to do some room temperature test or some ex situ experiment in a lab? Actually, we can infer the property and mechanism from those.
Well, I think you share my opinion, and I think these sort of tests are vital. I mean, the thing is that most of engineering has been based on doing a coupon test the size of your finger or something like that in the lab and predicting the large thing in reality. But with these composites, you can't do that because the geometry of these things becomes very important in terms of the fibers and so forth. And so it's very difficult to use coupon tests to actually predict reality. And so I think this is what Brian Cox would always push when we worked on that program, was that you needed to do high fidelity coupon tests. You have to do them, but you want to make them worth their while. And I think if you're dealing with these materials, and we're talking about temperatures which are, well, now they're at 1200 or more, but they can certainly go higher with these materials. You have to do them in real time, as you know, because if you want to get mechanisms to do the modeling, then you'd have to cool them down and then section them to see what's going on. And of course, everything's changed at that point. So you need to do this in situ. So the notion of doing real-time high temperature tests is vital. And we developed this facility, as you know, in about 7 years ago. And I've been surprised that no one else seems to have done this, because I think these tests are kind of important for, well, obviously the aerospace applications and the ones that you deal with a lot, which is the nuclear applications of similar, not quite the same material. But I think you need to do an in situ test at temperature, and the ability of the tomography is that you can see through the material. If it's a ceramic, you have a strong enough X-ray beam, and you can quantify everything you see, everything. And so it's a modeling dream in that regard. So I think I used to work with Rolls-Royce, and they didn't use this technique, and I think it made it very difficult to do the modeling, and because they didn't really know what the various different mechanisms are. So I think there's a tremendous opportunity there to get into some of these more complex materials and to model, at least to understand what the mechanisms are. And then that's the basis for modeling, which would then be the basis of a more realistic life prediction. But without the mechanistic understanding, it all becomes empirical. And I think it's a little bit more hazardous. So the in situ high temperature and presumably environment as well, you're probably interested in putting hot steam in as well or something like that. That needs to be done, and it's fully tractable. I mean, those little cells that we talked about are just like little testing machines, and we can just put them in the beamline, and as you've done yourself in the toughness tests in graphite. So I think that's a really important thing for the future.
Yeah, yeah, because I think that as much as we do lots of room temperature tests, the mechanisms are really never the same as the high temperature ones.
Well, they're completely different. Yeah, right, in a lot of these materials.
Yeah. Thank you very much.
Thank you.
All right, thanks. I know our EML editors are waiting patiently, but let's invite our guests first. So Yujun Xie, she asked the question in Q&A. Yujun, are you able to unmute and ask the question yourself?
Oh, yes, I'm here. Oh, hi, Robert. So I didn't prepare. So I'm a postdoc in NSAM. I used to talk to you. Now I'm working for Peter Horstman's group. So I'm just kind of interested in the number of medium range ordering, how they change with the ductile and brittle transaction. And is it is already very known in the field. And also,
I'm sorry, you talk a little fast.
Oh, sorry. So I'm right now I'm postdoc in NSAM and also work for Peter.
But what was the question again? You said
so the question is that we are interested in the number of medium range ordering, how they affect the brittle and ductile transaction. Is there any questions still exist in the community? Because I see a lot of work already reported that. But I'm afraid, for example, the focused iron beam like damage the sample and a lot of things that I think there's a lot of things we can do, but I just want to hear some opinion from you.
We don't know a lot about what short range order does to the ductile brittle transition. In the FCC materials, of course, it's not relevant, but in the HCP materials and the BCC ones, there is a question there, but we don't really know too much about that. What we've been doing in the FCC materials is to show how short range order can affect dislocation motion. And of course, the ductile brittle transition is really a question of having whether a bond breaks at the crack tip or whether you emit a dislocation. So I think there's probably that would be better studied in some of these BCC structures, which do have a ductile brittle transition. We don't know what that is. Most of the materials we've seen, these are the refractory high entropy alloys, have single digit toughnesses up to about 13 or 1400 degrees centigrade, because they're all refractory materials, and they sometimes can get a bit of ductility at room temperature, but not often. And then when you get a little higher than that, and this is becoming beyond the range that we can test metallic materials at this point, they probably undergo a more ductile, and that's a relative word, behavior. I looked at molybdenum boron silicon a few years ago, which was an alloy which was suggested for a replacement for nickel-based superalloys. It's too heavy, that's the problem with it. But that behaved like a brittle material until you got to about 1350 degrees centigrade. And then it started to generate a more ductile character. And I think you start seeing blunting at crack tips because you're emitting dislocations. Before that, you don't. Now, how order really affects that, I don't think anybody knows at this point.
How about medium range ordering in metallic glass?
Oh, in metallic glass. Yeah, I haven't really looked at that too much. I mean, the ductile brittle transition in metallic glass is the glass transition temperature in many respects. So, so we've not systematically looked at. We should do that. It's a good experiment, actually, to look at a glass where you can change the temperature and see that, to look at that behavior. So we've not really looked at that. I don't think, I can't immediately come to recall who has in the glasses yet, but that's an interesting thought.
Yeah, thank you very much. So yeah, so I think I'm about to do it, try it in the NSAM, but I think I can talk to you later. Yeah, if I have a chance.
Well, we're not on campus anymore, but next time we come, you can just wander over to my office. That's fine. Good.
Thank you.
Franz has a comment.
Yeah, Rob, you were wondering if people looked at ductile to brittle transition. Years ago, we're talking about the 80s now. We did this on metallic glass ribbon. There were some of them when you anneal them, they become brittle. And so we just measured, ductile to brittle transition temperature for a bunch of.
Yeah, but there's not really been looked at that closely recently.
No, that's true. But the phenomenon is there, and it depends on the alloy.
Yeah.
And to get into the question that just came up, the business of medium range order, the whole business of exactly how the shear occurs, even if you have in the right short range order, you have to couple in the neighbors in order to get sufficient shear. You can't do it with one atom, right? So for that reason, you have to go a little further out, and maybe there would be something interesting in knowing what the short range order is beyond just the first shell.
Yeah, I was thinking the question was on high entropy alloys.
I understand.
So but it is I mean, that is a tractable experiment to look at, certainly, whether it's really the single versus multiple shear band notion, and then the ramifications of where that comes from in terms of local order. Yeah. So I missed all that. I wasn't working in glasses
Yeah, I was just pointing out that it is out there for some of them.
Can you send me that paper, Franz? I'd love to see that.
Sure. That's Tsai Wu did that. So he did a very nice job on it. So now they have you on the short range order. Your diffraction guys, have they gone out the high temperature, the high entropy alloys and tried to get sort of standard, short range order parameters for all of that?
Yes. There's people trying to do that. There was this Mitra Tahira from who used to be at Drexel, has gone to Johns Hopkins. She's trying to do the X-rays on this now. Right. And we're trying to give her the same samples that we looked at so we can verify this. And one of the issues that came up is that her initial studies, and they were initial, admittedly, didn't reproduce what we had because we'd given her thicker material, and that got us worried whether, the short range order is always there, and maybe you can suppress it in a really rapidly quenched thin film. So we're looking with Teresa Pollock at splat quench material now to see if we can see that. But yes, the X-ray studies are the next one. And Mitra hopefully will have some results fairly soon. So I think with this, that no one's going to fully believe this until with 3 or 4 different techniques in different labs that have come to a similar conclusion. But, anyway, we'll be out. That is being looked at, certainly.
Thanks, Franz. Next, Junsu.
Hi, my name is Junsu. Thank you for the wonderful talk. I am PhD student in Jigang source group. So I'm interested in the extrinsic, intrinsic categorization of the mechanism. So mostly the extrinsic mechanism were made of fibers. And according to the length of the fibers, it could be extrinsic or it could be intrinsic if it is small enough. So my question is, in order to be extrinsic or intrinsic, what would be the characteristic length that defines intrinsic or extrinsic? Because when I read about the Naker projects, the composites, they said, oh, smaller nanosheet is better than macro scale. It seems quite related to the size of the fillers, or maybe related to the length, characteristic length that defines the extrinsic or intrinsic. So
I can see. Now, in my way of thinking, if you've got fibers in a material, and if those fibers stretch and then break ahead of the crack tip, then those are in damage mechanisms, and how you resist that in the material by associated with the length of the fiber or its bonding is the intrinsic mechanism. Once if those things don't break and get in the wake, then they become an extrinsic mechanism in that they can generate not necessarily plasticity for intrinsic, but they can generate some form of shielding of the crack tip. So it's a different mechanism. It's reducing the driving force effectively. And what's different is that most plasticity mechanisms, however they come about, be them from dislocations, microcracks, collagen fibrils in bone, are generally small scale entities. And so the intrinsic mechanisms, the length scales that generate the plasticity, are often pretty small length scales. It's not necessarily a requirement. It's just that the main effect of intrinsic toughness in my world is ahead of the crack tip and an inelastic mechanism. And most inelastic mechanisms find their origin at nanoscales. Once you get to extrinsic, you're dealing with phenomena like deflection, wedging, and bridging. And they can occur at any scale you want that you happen to have in the material. If you're dealing with some of your materials, the bridging of the fibers could be very, very small scale. Yet in bone, you're dealing with osteons that are separated by 200 microns, and you're getting bridges of those sort of dimensions. So there's no simple length scale requirement for extrinsic. But I think there is a sharp delineation. Obviously similar processes are involved in the generation of both types of mechanisms, but extrinsic are shielding mechanisms primarily. And intrinsic mechanisms are an inhibition of damage mechanisms. And there is a distinction there, I think. But as I said, what I know about hydrogels, you can put on the back of a postage stamp, so I can't really comment. But I mean, I think I can understand that in some situations it's a little difficult to make that delineation.
Thank you so much.
Maybe I should talk to Zhigan some more. So
I always.
You're a brave man to study fatigue, Zhigan. Your citation index will drop precipitously if you study fatigue. No, very, very poorly. Papers are always on fatigue are always very poorly cited. The engineers like them, but the scientists don't. So
brave men study fatigue, and the women. Next.
Oh, sorry, I beg your pardon. Yes, absolutely, brave players.
Sulin.
Hi, Rob. This is Sulin from Penn State. I think I met you in person when you gave a talk in Penn State. I don't know, 5-6 years ago in material science.
Right. Yeah.
Yeah. So a fascinating talk. I'm particularly fascinated by your comments on the characteristics of biological materials. One is a gradient, the other is adaptiveness. So you mentioned that it's made difficult to evaluate long-time evolution biological materials, but you know that general biological materials always undergo this short-time range remodeling. I consider this adaptiveness under different gradients. We talk about stress gradients or chemical gradient, right? So could you further elaborate on how these gradients interact with the adaptiveness or remodeling to work together in biological materials, especially say bone healing, right?
Well, again, you've asked a question I've not studied directly. I think that's an interesting point. It's a bit like Flavia's question. It's the question of whether remodeling of a material can generate an improved structure in a lifetime of a particular tissue or entity. I honestly don't know the answer to that question. But some of these evolution, I mean, I think the mantis shrimp is one someone mentioned, that used to spear its prey, and then it's developed a means of clubbing its prey. So these things happen, but I don't know a lot about how remodeling of a tissue in a structure can change, can adapt its function over the short time. I really don't know. So we've been intrigued by how nature develops certain sets of properties, but we you know, and I think the notion of hierarchical structures, and I think gradients are just terribly important in this regard for generating combinations of properties. But I really don't know too much about how that organism can remodel to improve that over a period of time. I just don't know enough about that.
So for instance, your bone, you have a fractured bone. Also, you generate a stress gradient at the crack tip, right? Would that induce some healing process going on at the crack tip? Did you look at that kind of problem?
Now that's, you know, but the time scales are a little bit difficult to get at. My particular feeling about bone fracture is that most of them are fatigue fractures. I mean, the medical community doesn't think that, but I think a lot of, when people say when they get old and they fall and break their bones, I believe that their bones are breaking and causing them to fall. The fatigue is the dominant failure mechanism in virtually every other material, not ceramics perhaps, but every other material except bone. So I think the fatigue is the next generation of bone people have to face up to that reality. And the problem with that is, though, fatigue is something that takes time, and what is remodeling taking place at the same time? And that's the issue. So if you do a test on dead bone, you've factored out one very important repair process, is what you're talking about. So the only solution to that is to do fatigue tests on live animals. And that brings up all sorts of ethics issues. And we tried to do this, and I wrote a paper on this on fatigue and of bone on this topic. And the trouble with it is, when you do a fatigue test on a live animal, you have to anesthetize them then you do the test, and then you have to sacrifice the animal afterwards. And there are limits on how much stress you can put on and how fast you can do these tests. And we don't really know the timescales involved. Is the remodeling process taking place at a relevant timescale while you're doing this fatigue test? And these are all unanswered questions. But what we can say is that when you do the test on the live animal, where you can compare it with a corresponding test on a dead bone in an appropriate environment, that the live animal test should last longer because of the repair processes, and all the data shows the opposite. So this is a very, very important question, but it's a very difficult one to answer because you really need a living tissue to do it. It's like doing a stress corrosion fatigue test where you're setting the frequency for the mechanical loading, but you have no clue how fast the corrosion is taking place. Well, the same thing is doing here. There's a repair process presumably taking place in the bone, and we just don't know the kinetics, how it compares with the mechanical damage. But I think that the bone community is going to have to come to terms with that somehow, because I think that is the really important aspect of bone fractures, that they're not instantaneous fractures, they're basically occurring in time. The only people who seem to have gotten some insight on that are the racehorse people, because they know that a lot of racehorses have a lot of fractures. So they've got quite a lot of information. I haven't really tapped into that, but I think that's the next generation of bone people have to come to terms with that.
Great, thank you for your comment.
Thanks.
That's one for you, Otman. You should deal with that. So
by the way, we just hired one of the Berkeley postdoc, young. I don't know if you are associated with him. Definitely, he's working under Andy Miner.
Mm-hmm.
Yeah, Yang is doing this in-situ TM.
Yeah, that sounds good.
Yeah.
Oh yes. Yeah, you mean Yang, right?
Yeah.
Yeah, luckily he's decided to stay with us for one more year just to good. He's very good. That's a good choice of person.
Yeah, exactly. Yeah.
All right, next, Tan.
Okay, this is Tan Li from University of Maryland. I'm also one of the associate editors of Extreme Mechanics Letters. Thank you, Rob, for this fantastic talk. I think your talk perfectly optimizes the essence of this webinar series. So to demonstrate that how mechanics can be used to help us to understand different materials, from engineered materials to biological materials, from traditional conventional metals to the high entropy alloys, and from bones to teeth. And yeah, so in other words, mechanics rocks. And in your case, it's fracture mechanics rocks. So I have a question about the later part of the talk on this high entropy alloy. So you showed that in this paper last year, Nature paper, and we replaced the magnesium with the palladium, right? So the distribution of the atoms, elements in the alloy becomes quite different, right? It's going from rather uniform distribution to a somewhat inhomogeneous alloy with this magic number of about 1 to 1.4, 1.5 nanometer periodicity over there. And later on, you showed another work, I believe it's with Andy Miner in a 3-element alloy. I remember there was another feature size, critical length about 1 nanometer came up as well. So my question is this something more universal length scale over there? And what's your insight of this length scale of the feature there? And well, what's the indication to the mechanical properties?
That's an excellent question. This is what was asked earlier about whether there's hierarchical scales of short range order. I was surprised how little is known about short range. I didn't know a lot about it and so forth. But I think what we were looking at with Andy Miner was the interaction of the inner shells at first, and so you're generating a very classical short range order with a length scale of about a 0.5 nanometer, and I think that's effectively the question of whether the chromium atoms or cobalt atoms like similar atoms or they don't. And we seem to think that unlike atoms seem to be more important there. There's also a magnetic effect. It's a magnetic frustration effect with this system as well, which we're looking at, which may be the dominant reason for the short range order. But that's classic shape range order that Andy looked at in those experiments. The ones that were done on that earlier paper were more longer range, and you know, this notion of concentration waves, and you're getting a little bit from a half a nanometer up to, I said 10, I should have said about 1 to 3 nanometers, and that's a different animal in many respects, and it's not surprising when you take out a magnesium atom, which is nominally the same size as its other ones, and stick in a big palladium atom. But we were just trying to prove a point there. So I think Yu Qian's experiments do show that these concentration waves are quite feasible in terms of a degree of ordering there at a coarser scale than what we looked at in the nearest neighbor approaches. But again, the question is it going to have an effect? Now, we talked about in that earlier paper the roughening of the lattice and so forth, and this is a concept of increasing the resistance to, you know, the lattice distortion and the lattice resistance, but we didn't have any measurements of at that point about the mechanical properties. In Andy's case, we did do the measurements, but again, they were all thin film type measurement with small section measurements, and so I still don't fully understand whether these local ordering are so significant as we'd like them to be. But there's certainly different length scales in those two papers there are a different degree of ordering, and there may be even more. You know, people have talked about spinodal decompositions that can be put in here. So there's all sorts of interesting aspects that we need to look at. We're just I mean, we're funded by the Office of Science in DOE, so they just want science. So that we don't have to show that it's important from a properties point of view. But I think that's the intriguing part here. Does this order exist? Why does it exist? Is it on multiple length scales? And really, does it have much relevance to the mechanical properties? And we think it does, but I know others think it doesn't. So the jury's out there. But these alloys are very interesting, though. I think they are. Some of them show really extreme properties, and some of them don't. And there may be other ones out there which are intriguing, but certainly these ones, the cobalt, chrome, nickel, do show things that are different. And I think when we write papers on this, we say we see so-and-so and this mechanism and that mechanism, and people will say, well, yeah, well, that's been seen in magnesium in 1980 or something like that. But the thing with these high entropy alloys is you get a bigger bang for the buck. You get multiple mechanisms that take place simultaneously that give you these interesting combinations of properties, and they seem to be much more extreme than we've seen in just sort of the dilute solid solutions that we're used to. So I think there's a lot of intrigue to look at in these materials in that regard. A lot of people now are going in and adding a dab of this and a dab of that to get better properties, and that's intriguing research, because some of these things do get slightly better properties, but that's really not, we can't redo that for the Office of Science. So our attempt is to see if there is unusual science in these materials and whether it has any predictable or any relevant effect to the mechanical properties. I think it's an interesting thing to look at anyway, whether you believe it.
I think you mentioned this, the challenge. I guess this challenge also somewhat is limiting our understanding of this new group of new set of material, because of this manufacturing process is not mature enough. So you either have a small scale or a thin film. So probably, I think the findings, your papers show that this certain length scale matters will bring in the new insight in this. For example, if we manage to manufacture large scale samples, I don't know, there might be some other mechanisms which is not clear for now at the small scale. Currently, people basically play with different elements, right? The concentrations, less, more. Yeah.
I think you're right. That's a modern trend of research in materials now, is to, when I was started, everything was done with tensile tests and this kind of thing. And now we do have a better experience of length scales. And I think you can learn something about that. I've always been intrigued by the MD people. I remember people did MD calculations on ceramics and predicted that fine-grained ceramics should be tougher than coarse-grained. And that's exactly the opposite of what you would actually measure. But of course, the size of their MD calculation was smaller than a grain. So you'd never see these things. And I think that this sort of information is a bit funny initially, but it does help you build up a picture. So, and I'm also been intrigued by the fact that certain properties originate from specific length scales. I remember listening to somebody in Japan saying that bone was a nanocomposite. They were going to make a synthetic bone, but bone is a nanocomposite, it's a microcomposite, it's a macrocomposite, and it's a mesocomposite. And each one of those length scales, it derives different properties like many biological materials. And I find that very fascinating.
Thank you.
Thanks, Tan. Next, Otman Tertuliano.
Hi, Otman, how you doing?
Hey, Rob. So I guess I was a grad student with Julia Greer at Caltech, and now I'm a postdoc at Stanford. Thanks for the talk, Rob.
We all make mistakes, of course, but there we are.
Sorry, come again?
We all make mistakes going to Stanford, but there we go.
Yeah, I think in essence, you've answered my question from your conversations with a couple of different people so far, but ultimately I wanted to ask you about how we think about fatigue in bone, and you've touched on this really tricky conflict of timescales and the idea that, Shulin brought up, bone is a living material that remodels, and that's not something that we encounter oftentimes with our engineering materials. I'm wondering if it's something that I want maybe your take from an experimental perspective. I wonder if understanding fatigue mechanisms in bone can be something that we tackle by focusing on different length scales. So the issue is a time scale thing, because these osteoblasts come in and they'll help remodel based on stress gradient, pre-existing flaws. But that remodeling occurs on different time scales over different length scales. And I wonder if we can focus on different length scales in this ridiculous hierarchy of bone to sort of fight that time scale problem experimentally.
Maybe. I mean, I think this is something that people like you and Flavia are going to have to determine with, but I think it's a terribly difficult problem, because I don't know. I mean, we were trying to design experiments to do the live tissue bone, and what frequency do you use, what loads do you use, and we just hadn't. And the frequency defines the length of time of the test, and we had no concept of what our remodeling rates would be and this kind of thing. As I said, it reminded me of doing a corrosion fatigue test and not knowing whether the material is going to behave like titanium and oxidize in a microsecond, or it's going to behave like steel and oxidize somewhat slower. It's that kind of scenario. So I think these are very difficult things, and you can't increase the load that much with a live animal to get the test to the scale you want. Now, how length scale plays into this as well, I think that's probably a somewhat easier problem, because you could do that. You wouldn't have to use mechanical force to do that. But again, these things are all coupled. So I don't know how you do these experiments, but I think someone has to do them if they're going to really understand. I mean, fatigue to me, I made the comment that doesn't get many citations, but it is the essence of failure of most materials, and I don't think bone's an exception. And I think if you could isolate length scales, that would be interesting, but you still have this problem of the time associated with the remodeling process. And by isolating length scales, you're going to kind of affect that rather significantly. So that's going to be a difficult experiment. It's something that I think someone's going to have some really bright ideas to deal with it. I mean, the other thing is that the remodeling of bone is fatigue. It's fatigue loads, it's cyclic loads that inspire remodeling. So, and there's some classes of people that are trying to come up with ways you can regenerate bone by vibrating yourself, right? You stand on a scale that vibrates, and then, but I think the realization now that the vibrations you need to be significant would probably kill you, so that wouldn't be the best thing. But I don't know the answer to this question, but I know it's a question that needs to be looked at if we're going to progress in the understanding of bone fracture. So I think the kinetics of the remodeling versus the kinetics of the mechanical damage is the real important question to answer, and that obviously length scale will play into that. But I think that first issue is at this point more important. That was my personal view. Didn't really answer your question, but I think these are the liberations that we all have to think about. At least you guys have to think about.
Yeah, it is an issue that there's no, well, yeah, we should look for that answer. I kind of want to follow up by maybe tying the two parts of your talk. You spoke about these two very complicated sets of materials, biological and metallic. Bone is kind of an interesting one because it is a system that we and doctors have decided to enhance and implant metallics, titanium alloys, the total hip replacement, for example. And this is something that we've been doing since the 60s, actually, and it hasn't, the technology hasn't really improved for the total hip replacement. It still fails due to these material mismatches. I'm wondering if, throughout your studies of looking at these two very different materials, you start to see maybe a way in which we can get these material properties to converge, and perhaps start thinking about, designing these metallic alloys to fit better with these biological materials.
Yeah, you're right. There's a lot of work in that regard. In fact, the irony is that I think the average life of a hip implant is probably diminished in the last 15 years rather than gotten longer, because a lot of these attempts to do things have not worked very well. So, the story, of course. People tried to use ceramics to prevent metallic wear, and that caused a lot of premature failures, and the notion of coating with hydroxyapatite and so forth. So there's a lot of issues here. The stress shielding one is, of course, important, difference in the modulus, and that's one that I think people are getting a better handle in. There's some lower modulus titanium alloys that have been developed, and the use of porous materials could reduce the stiffness, of course. The corrosion one is better because the original designs were Chandley stainless steels, and of course, they work beautifully in some materials and corroded like hell in others. So I think we have better handles on that. And then of course the notion of having these sort of porous structures where you can have a change in the pore size to bring in more tissue, to give a biological bond. These really have not been overly successful, but the bottom line is that orthopedic surgery is a pretty successful process, but no one's really done a great job in enhancing beyond 15-year lives, right? And if you have one of those things put in your hip too young in your life, you're not going to have enough tissue by the time you need the second or third surgery. So that is an issue. I've not studied a lot on orthopedic tissues, but I've seen some of the disasters that have happened. And one thing I do think people forget, a lot of people have designed structures. They've used 3D printing to design structures where you can adapt the structure to have, if it's a framework structure, to have more frameworks where the stresses are higher, where you need higher stresses, and to sort of to have an implant which is geared to a specific person. And this is very clever. You can do this with 3D printing and so forth, and some of the companies are doing that, but they forget that fatigue cracks start because the surface isn't perfectly smooth. And a lot of those examples have actually been very much of a disaster because they haven't realized that there's some of the more basically simple stuff, like making sure you haven't got notches or rough surfaces, have been overlooked. So I think there's a potential there, but the recent history has not been overly successful, I have to say. And a number of companies now, is one that's making all their orthopedic implants with 3D printing. Now, this is obviously economically a great idea, but you know, can you really control the quality of the material and the quality of the surface with these additive manufacturing techniques? And so I don't know the answer to that question, but superficially, I think that's an accident waiting to happen. So.
Thanks for your answers.
All right, next we see a new hand, Zhe Ren.
Hey, Professor Rich, and thank you very much. Actually, many of my questions have been covered by this excellent panelist and your communication with the attendee. I'm a material research engineer from Phoenix, a startup devoting to design a permanent magnet. And I graduated from Case Western University last year. My advisor was Frank Ernst, and co-advisor was Arthur Hoyer.
Really?
Yeah, so I'm especially interested in your presentation on the property of the biological material. And I think finally, we scientists and engineers want to learn from nature and trying to infuse our learning into you know, design that can be beneficial and finally commercialized. So to people, like, so I'm wondering how those biological material can shine light on the biomimetic material, like artificial material. And can you share some experience or story on that? Like how the scale study can, you know, impact on the armor design, or how the scan can influence on the artificial skin design and the bone on prosthetic, you know, bone design, something like that.
Well, I think these things have gone on in parallel. For you look at people who designed armors for a long time, and when you look at some of the polymer composites, you realize that nature has been doing the same sort of thing. So there's not always a cause and effect. These things have happened simultaneously. But I do think that things are becoming clearer now by looking at sort of biological systems. We know a little bit more how nature can deal with armored systems. We know we know a little bit more about how nature can generate like the mantis shrimp appendage, where you've got really hard and materials at a certain structures. That's the easy bit, but we've also talked about the remodeling and repair. And I think that's the more difficult thing that we have to deal with, whether that's ever feasible in a synthetic material. But that mantis shrimp generates this ridiculously strong, hard material, and it can club you know, some mollusk to pieces in a short time. But that structure can repair itself very quickly too. And I think that's the more difficult problem. The things that have appealed to me in terms of nature, and we've tried, you know, it's very difficult to make these structures, there's no question. Even nacre, which is a simple brick and mortar structure, is very difficult to make it in the form, shape, and size scales that are perfect for how nature does it. And I think that's where the 3D printing, or which is a bottom-up technique where you could actually build a structure like that. If that ever becomes feasible, then we could probably adapt them more. But I do find that everybody knows about the hierarchical structures, and I think that's important because it can generate different properties at different length scales, and that gives you interesting combinations of properties. But the thing that's most impressed me about nature is the gradient thing, because I think the way that it deals with gradients, you can get very unusual combinations of properties. And I think that's the thing that we don't do as well synthetically. I mean, just you know, bamboo and it's being very stiff but very flexible and very hard, and all these sorts of things are just fascinating, generated by gradients in structure, gradients in composition, gradients in properties, gradients in form. I find that's really very interesting, and that's something that we could harness more in our synthetic materials if we could make them easy enough, and that's one of the issues. And then the final thing is the fact that a lot of these structures are smart structures. They can adapt under load, like the rotation of the collagen fibers. These are fascinating mechanisms, and whether we could ever generate those synthetically, and if it was possible, allow them to repair. There are people that have done damage repair in polymers and so forth, but I think there's a lot of potential excitement in trying to copy nature in that respect. The structure, just getting the same structure is the easy bit, and that's been done. It's the more difficult bit. So how we make those graded structures and how we can get them to adapt under certain conditions. I think that's an interesting aspect, certainly.
Thank you.
Good question.
To follow up on that, Rob, you talked a lot about bones. How about skin? You mentioned that there is a lot of smart adaptiveness for the skin collagen. And we also see like in polymers, when they get highly stretched, they also have this alignment of the polymer chains, right? So some of those adaptiveness are passive purely because of mechanical loads, but there are also, for biological materials, there are also active adaptiveness. So is there any possibility that we can also engineer some of those active adaptiveness into our structural materials?
Yeah, well, I mean, that's the challenge. I think that's a good point. It's certainly a challenge to do. I mean, I think, but with all these things, you've got to make the materials as well. Maybe polymers are easier to deal with because they can be. I think the 3D printing notion in polymers is much more realistic than what might be in a metal or something like that. But these are, I think that's a very good point. These are certainly the way that hopefully things will go. And I think that's the excitement of looking at nature, because you know, it's how can we adapt those into structural materials or into synthetic materials in a feasible and practical way? And there's all sorts of questions there. But I think that's been an inspiration in the field of structural materials over the last 10, 15 years. And in fact, our friend Art Hoyer was one of the first people to look at these things. It's I think these are very exciting things to do. And now the question is, okay, the science is interesting. Can we make it useful? And that's the question you've asked. And that's a very good question.
I just want to make a comment here, Rob. We look at your paper in Nature Communication on skins. You test the skins. You talk about in front of a crack tip. You have rotation, alignment, all kinds of elementary movement of the fibrous as a toughening mechanisms in front of the crack tip in skins. So we recently look at the skins of plant cells. It's like a skin.
Yeah.
The fundamental mechanism is very, very similar, because really? In the so plant cells has a lot of cellulose fibrous, and under stress it will get straightened, curved, straightened, rotate, and sliding, all kinds of elementary movements. Yeah. Will appear. So it's very similar. So I read your paper. We're going to cite your paper.
I'd like to read that when you send it up. I mean, I think that's what's so neat about being able to when you're young, you sort of have to work on the fields that you're strong at to get your position. As you get older, you can spread your wings a little bit. And I think that the commonality of mechanisms across very different systems is just fascinating. I've always envied the people who are the beamline scientists that are at synchrotron, because they get to work on all these different projects. And the guy that followed me doing on the ceramics was someone who was looking at water fluid through plants. And, you know, I think, as you point out, there's a lot of commonality about these things. And I find those connections really very interesting in science.
We are writing a manuscript. I'm going to send the manuscript to you upon the agreement with my collaborators.
I'd love to read it. I'd love to read it.
All right, Zhigang.
Yeah. Hey, this is a fantastic talk. It's just a wondrous celebration of how human and nature to find their way to toughness. When I ask you to give a talk, I hope to hear your view on fatigue. We'll have you give another talk. So,
the trouble with fatigue, I'm too old for fatigue now. I'm not sure I can live out the experiment. That's the other issue. I know you've become the fatigue man now, so with your hydrogel.
A couple of comments. I'll first report some news to you about fatigue. Fatigue is such an exciting area now. Let me tell you why. because recently, a couple of us, my group and a couple of our people, developed a material system. For example, give you a concrete example, natural rubber. Natural rubber has a fatigue threshold about a 50 joule per meter squared, 50. That number has been known ever since it was measured about 60 years ago, has never been improved. But rubber itself under monotonic loading is extraordinarily tough. Toughness is on the order of 10,000 joule per meter squared. Huge difference, just like metal. Now, recently we have found a way to make elastomer of a fatigue threshold beyond 1,000 joule per meter squared. And that principle is general. It's not just about rubber. It could be metal, could be ceramic, could be composite, could be anything. So if you're interested, I'll send you the paper. We actually have a couple of papers.
Certainly, yes.
Yeah, it's a general principle. It's a step upon. It's an exciting field now, fatigue, because we can make change, make difference. But go back to toughness. We'll ask you to give a talk on fatigue at some point. So it's just such a wonderful talk. Now, about toughness, I want to actually have a conversation with you. I think there is a common misunderstanding, or I would say repeated by you today, and repeated by myself in my lectures. So I just want to have a conversation with you. I try to be provocative. Now, let's compare two materials both you and I are very familiar with and very successful. One is a ceramic matrix composite, which you covered today. The other thing you didn't cover, but you must know very well, that is a polymer matrix composite. Polymer matrix with either carbon fiber or glass fiber. Two extraordinarily successful materials in applications. Both are very tough, right? But their design principle superficially look different. For ceramic matrix composite, we always we need to have a weak interface, have a fiber sliding. And we say, today you said it again, the fiber sliding will dissipate a lot of energy. That's ceramic. For polymer matrix composite, people actually designed it with very good bonding. You do not have debonding, you do. So do you have do you see these two things as a different kind of a toughening mechanism, or they're essentially the same?
Well, no, I mean, if you take a metal matrix composite as well, you generally want a strong interface there, and in metallic composite with a ductile phase, you want an intermediate strength interface. So one shoe certainly doesn't fit all, and the two you explain are the polymer and the ceramic composite are completely different. They fail in different ways. I mean, the polymer composites really are not single dominant fraction mechanics style materials. They fail by distributed damage in many cases, I think. So not always, but so that's a different animal. The ceramic composite could go that way as well. So you've got that issue, but the concept is you add reinforcements to a polymer primarily to increase its stiffness, right? And then you get a benefit from its strength and toughness. But the question with a ceramic composite, the main issue is you have to deal with the brittleness of the matrix. And really the driver for this has got nothing to do with toughness. It's the need for ductility. Designers, when they design something, want ductility. It's their parachute. If they make a mistake, the material still holds together. And so the main reason I think that drove ceramic composites is that the matrix is going to fail catastrophically because it's a ceramic. Now that would not be the case in most polymer composites, but then the fibers can just hold the material together until they break. And so that gives you a region. You wouldn't use the material in that region, but it gives you a region between the matrix failing, which is the non-proportional limit, and the fibers failing, which is the ultimate. And that's the fake ductility that gives ceramic composites, the go-ahead to be used in in a safety critical situation. They don't just fail like that, like the matrix, because the fibers hold it together. That's a completely different concept to what you're doing when you're making a polymer composite. You have a polymer, there's various different types of polymers, but they're generally not super brittle. And then you put a fiber in to increase the stiffness, and you put the fiber in different orientations to get a different anisotropy or isotropic properties. But there's a very different situation. And the stiffness, if you don't, you need the fiber to be strong in comparison with in the interface with the matrix to get that stiffness. If you don't have that, you get hardly any stiffness benefit at all. So there's a very different concept used for both those materials. So one has a weak interface because you want bridging to give you ductility. The other one, you generally have a strong interface because you want the stiffness. And the metal matrix composites have the same thing. Metal matrix composite, you add sort of a silicon carbide phase, you increase the stiffness, you increase the hardness, but the toughness drops like a stone. So you've got to, so it's, there's just not one shoe fits all for these things. But it is intriguing, right? That one system goes for weak interfaces, that's the main driver. The other one goes for strong interfaces. So.
Yeah, so let's focus on this these two type of composites. Let's say we do standard fracture test for both composites, polymer matrix and a ceramic matrix. I put big crack, I make a big crack, and then I pull this until it fractures, right? I do same experiment. So I can certainly do this fracture toughness measurement. People do that, and both materials are tough, comparable toughness. Whether you're polymer matrix or ceramic, it doesn't matter at all. So the reason now we understand that has something to do how we make material fatigue resistance as well. The reason is actually very simple. These two materials are identical in the following way. Because both materials, we all know, have very strong fibers. I want to discuss with you. See, this is a view you can accept. So both materials we know, just in making materials, ceramic matrix or polymer matrix, the fiber themselves are strong, have high strength, and very elastic. No plasticity with fibers in both cases, right? Rob, you agree with that, right? Yeah. So now if you have a crack, let's say go to ceramic. You and I studied this before. Ceramic. What happens is we know ceramic matrix and the fiber debond, allow fiber to deform. Because you have a debonding, you can distribute a high stress over very long distance. So in the limiting case, Tony always said, if you have zero shear stress, the composite will have infinite toughness because the entire fiber is stressed. So you actually don't want to have any frictional sliding. So that's a ceramic matrix composite. If you look at a model, that's what model told you. You actually want zero dissipation due to sliding. Now, for polymer matrix composite, story is the same. So now you have a crack coming in, you have a fiber, because the polymer itself is soft. You can distribute high stress again over long distance of a fiber, strong fiber. You don't have stress concentration. So therefore you get same toughness, because once the fiber break, you release stress over long distance. You do not have stress concentration or distribute stress concentration. Significant. So these two composites actually follow the same principle. It's also the principle followed by Naker. Stress deconcentration. So this is what we realized recently. We try to reconcile these things. This is a conversation, but
yeah, but in both cases, whether you get an interface failing in a ceramic composite versus the matrix flowing, allowing the motion, you have a limited process of inelasticity, which allows the dissipation of high stresses, and that really is the essence of toughness.
I think you're right. Stress deconcentration. It came actually back to your advisor's advisor, Your advisor was Cottrell, right?
But John, not my advisor.
Yeah, Cottrell.
Cottrell was my advisor's advisor. That's right.
Yeah, advisor's advisor. Cottrell actually wrote an earliest paper, as far as I could tell. Essentially, was a paper about this bridging, not bridging model, shear lag model to distribute stress, high stress over long distance. He was the person actually produced that model in early 1960s.
Yeah. Okay. I thought. Yeah, that wasn't Kelly. It was Cottrell, right?
So Kelly, in his review, he said Cottrell wrote that paper, wrote that model for him.
But I think what you've described is the essence of toughness, is that you need inelasticity, but you need limited inelasticity. If you have too much plasticity base, you have a soft material. So you've got to have limited inelasticity coupled with strength to give you toughness. And my intrinsic and extrinsic is really saying, where does that occur? So, if I'm talking about bridging of fibers behind the cracked tip, that enableization to do that is a function of the interface or the boundary between the fiber and the matrix. And I just think it's how exactly that occurs, whether it occurs precisely in the interface, like you might have in a ceramic composite, or it involves flow in the matrix like you have in a polymer composite. And in fact, when we've made these nacre-like structures, it's much more potent to have that motion between the bricks in nature associated with flow in the metal or the polymer or whatever phase you use as the mortar, rather than an interface failure. When you have an interface failure, you get the inelasticity, but you get low strength. So there are combinations. If I know what you're driving at, that's a very important point.
Yeah, actually, Rob, I disagree with you about the plasticity. What you said, that you need to have plasticity and elasticity. That's the true in many systems, because the plasticity happens. But you and I know plasticity is a curse if you want to design against fatigue.
Yeah, but I think it's degree there.
Let me give you a concrete example. I think you will agree with me about a phenomena. So we also have one class of material, extraordinarily tough, have zero plasticity or almost zero. That is elastomer reinforced by wires. You can use wires that has no plasticity. And that material is very tough. The reason is very simple. This elastomer being elastic and very soft can allow you to distribute high stress over long distance of wire.
Yeah, well, that's a better way of saying it than I said it. I think
so in the whole thing, you don't need to have a plasticity.
High stresses, right?
Yeah, you do not need to have a plasticity at all. That's actually essence how we design high fatigue resistant material. You deconcentrate stress using elasticity.
But what you just said, maybe in most real materials like metals and ceramics, you would have to have some inelastic process to be able to do that, I think, right?
Yeah, but for example, for ceramic matrix composite, right? The best material we all know, learning from Tony, is zero shear stress. Right? Zero shear stress. That you totally get rid of the plasticity. That is the toughest material, because you can distribute stress over really long distance. The moment you degrade that shear stress, you get brittle material.
Okay, so you corrected my terminology though. But these are mechanisms to dissipate high stresses. That's the kicker.
Yeah. So you and I need to have a conversation. So would you say you are willing to give a talk on fatigue at some point?
Well, this is the longest seminar I've ever had in my life. You're going to need to give me 6 months to recover, and then I'll come back.
Yes, we go. Yeah, it's a wonderful talk.
Thank you very much. Appreciate it. Thank you for all the questions as well. It's been absolutely fascinating. It's great to see you guys again.
Thank you.
It's tough being stuck in your room all the time. I can't even go to my office. That's the bad thing. And I'm just starting to be able to, I think I'm allowed to go in once a week or something. And so it's California is not the place it used to be. The air is foul, and there's
yeah.
stuff.
You have just showed that this toughness, the diversity, how things become tough. So it's just diversity, just one thing after another different. All things are different.
Yeah, I know. It's yeah.
Thank you.
Thank you. Thank
all
you.
All right, Nanshu.
Thank you, Nancy, for all your chairmanship or chairpersonship this morning. That was good. Appreciate it. And I really appreciate it.
Thanks, everybody.
So just before I go, this thing will appear as a YouTube, because Jim Rice wrote to me and said he couldn't make the lecture because he had to give his class, but he wanted a copy of it. So that'll become available then, will it?
Yes.
Yeah. The video will be available on YouTube later today. Yeah. Send it a link.
Wonderful.
Yeah, I'll send you a mail. Yes.
I won't be able to watch it. It'll be too embarrassing. But anyway, I can send it.
You'll take a beautiful talk.
Thank you so much. I appreciate it. You take care, guys. That's good.
Thank you.
Thank you, everyone. Take care.
Thank you. Bye.
Bye.